Welcome to the deep dive.
Yeah.
Today, we're going to be taking a deep dive into some pretty fascinating mathematical concepts.
Oh, yeah.
Yeah, h-Shuhan matrices, to
Okay.
be exact.
Interesting.
You've provided us with some excerpts from this paper titled Positive Determinacy of h-Shuhan matrices with h less than 2. And I had to say, even for someone who loves a good math puzzle, this looks like it's going to be a challenging but rewarding deep dive.
I think it will be.
Yeah.
Yeah, this paper really delves into the fascinating world of h-Shuhan matrices and how they relate to these generalized Cartan matrices.
Okay.
The authors really explore these different types of positive definiteness and how they apply to these matrices, especially when h is less than 2. There's a lot to unpack here.
All right, let's get started. The paper starts by defining these h-Shuhan matrices, and it seems like they have a very specific structure. Could you break that down for us?
Absolutely. An h-Shuhan matrix, which is denoted by 1i, is defined as a square matrix that must satisfy 3 specific conditions. The first is that all the elements on the main diagonal must be equal to h, which is a real number. So AH door for all dollar.
Gotcha.
Second, all elements off the main diagonal must be non-positive integers, meaning all A dollar for our.
Okay.
And finally, the matrix must be either symmetric,
Yeah.
meaning over for all other and dollar, or satisfy a specific asymmetry condition where over applies all other.
So these h-Shuhan matrices have this unique combination of h on the diagonal and then non-positive integers off the diagonal, and then this specific symmetry or asymmetry. It's like a mathematical recipe with very precise ingredients.
Yeah.
What makes this recipe so interesting? Why should we care about these matrices?
Well, that's where things get really interesting.
Okay.
These h-Shuhan matrices are actually closely related to generalized Cartan matrices, which are fundamental in the study of Lie algebras. And Lie algebras have far-reaching applications in physics, engineering, and other areas of mathematics.
I see. The paper mentions something about adding 2 tires times the identity matrix to an h-Shuhan matrix to get a generalized Cartan matrix.
Exactly. That's a key insight.
Huh.
Let's say we have an h-Shuhan matrix, $1 brown.
Mm-hmm.
If we add $2 times the identity matrix,
Okay.
denoted by $1,
Right.
we obtain a generalized Cartan matrix. Mathematically, this can be expressed as $1 plus 2 hours Jua.
Gotcha.
And this connection essentially means that h-Shuhan matrices can be seen as generalizations of Cartan matrices,
Okay.
offering a broader perspective on these important mathematical objects.
So it's like we're expanding the family of Cartan matrices by introducing these h-Shuhan matrices.
Okay.
We're adding another layer of complexity and potentially uncovering new insights into these mathematical structures.
Right.
The paper doesn't stop there, though, right? It goes on to talk about different types of positive definiteness. Can you explain what that means?
Yeah, of course. Positive definiteness is a key concept in linear algebra, and it's particularly important when studying matrices. Essentially, a matrix is considered positive definite if a specific mathematical expression involving the matrix and any non-zero vector always results in a positive value.
Could you give us a more concrete example of what you mean by that mathematical expression?
Certainly. Let's imagine we have a matrix dollar
Okay.
and a non-zero vector $6.
Okay.
The expression we're talking about is the quadratic form, which is written as 6 tax,
Okay.
where $6 is the transpose of the vector $6.
Fuck.
If this quadratic form is always positive for any non-zero vector $6, then we say that the matrix dollars is positive definite.
So positive definiteness essentially tells us something about how a matrix interacts with vectors.
Right.
And whether it kind of preserves their direction in a sense.
Yeah.
The paper mentions other types of positive definiteness as well, like virtual positive semi-definiteness and generalized positive semi-definiteness.
You're absolutely right. These are variations on the concept of positive definiteness. Virtual positive semi-definiteness refers to a slightly weaker condition where the determinants of certain submatrices are always non-negative. In simpler terms, it's like ensuring that all the building blocks of the matrix have a certain level of stability.
And what about generalized positive semi-definiteness? How does that fit into the picture?
Generalized positive semi-definiteness is determined by a slightly different mathematical condition that involves comparing the matrix with a specific type of matrix called a positive diagonal matrix.
Cool.
It's a bit more technical, but essentially it's another way of characterizing the matrix's behavior in relation to vectors.
So we have this whole family of positive definiteness concepts, each with its own specific definition and implications. Why is this important in the context of h-Shuhan matrices? Why are the authors so interested in figuring out when these matrices exhibit these different types of positive definiteness?
That's a great question. Remember that the paper focuses on h-Shuhan matrices where h is less than 2.
Right.
And it turns out that this restriction makes it more challenging to determine when these matrices exhibit the various positive definiteness properties. It creates a sort of mathematical puzzle where the value of h plays a crucial role in determining the matrix's behavior.
So the authors are essentially trying to crack the code of how h influences the positive definiteness of these h-Shuhan matrices.
Exactly.
Like h is the prime suspect, and they're gathering clues by analyzing different matrix types and their properties.
Precisely. And to solve this puzzle, they use a variety of tools and techniques. Throughout the paper, you'll see them using terms like lemmas and propositions.
Okay.
These are essentially stepping stones and intermediate results that help them build their arguments and ultimately arrive at the main classification theorem.
Could you give us an example of how these lemmas and propositions work in practice?
Yeah.
How do they help the authors piece together the puzzle?
Certainly. For instance, in Lemma 2.1, they establish a formula for calculating the determinant of a matrix that's formed by adding a scaled identity matrix to another matrix.
Okay.
This might seem like a technical detail, but it's actually a powerful tool that they use repeatedly in later proofs.
It's like they're forging a key in Lemma 2.1 that they'll use to unlock several doors later on in the paper.
Right.
They're building a foundation upon which they'll construct their main arguments.
And in Proposition 2.2, they use this key to show that if a matrix is virtually positive, semi-definite, then all its eigenvalues must be non-negative. This is a significant result because eigenvalues tell us a lot about a matrix's behavior and stability.
It seems like the authors are carefully constructing a chain of logic, with each lemma and proposition leading to the next, gradually revealing the intricate relationships between h-Shuhan matrices and their positive definiteness properties. But I'm curious, how do they actually apply these concepts to specific h-Shuhan matrices?
That's where the paper gets really hands-on. They introduce several specific matrix types, such as AN, B8N, DHN, AN, FH4, and GH2.
Okay.
Each of these matrix types has a unique structure defined by the arrangement of A and each ones and zeros within the matrix.
Okay.
And they analyze these matrices individually, exploring when and how they satisfy the different types of positive definiteness.
So it's like they're examining different species of h-Shuhan matrices, each with its own unique characteristics and behaviors. And by studying these individual species, they're hoping to gain insights into the broader genus of h-Shuhan matrices as a whole.
That's a great analogy. And one particular matrix type that they focus on is BHN. They introduce a new concept, n, which is defined as the largest real number that satisfies a specific equation related to the matrix Bn. And this n is a key player in understanding the behavior of Bn and its positive definiteness.
I'm seeing this in Lemma 3.4. It states that n increases as n increases, but it always remains bounded by h, plus a constant which is approximately 2.04998. It's like there's an invisible ceiling that n can't break through, even though it keeps growing as n gets larger.
Exactly. That boundedness is crucial because it tells us something fundamental about the stability of Bn.
Okay.
Even though might increase causing the matrix to grow in size, there's a limit to how much its behavior can change in terms of this n value.
So even though Bn might evolve as it increases, it's still constrained by certain fundamental limits.
Yeah.
It's like there's a hidden order within this seemingly complex system.
Right.
But the paper doesn't just explore individual matrix types, does it? It seems to culminate in this classification theorem. Could you tell us more about that?
Absolutely. The classification theorem, stated as Theorem 3.9 in the paper, is the grand finale of their investigation.
Right.
It provides a comprehensive set of necessary and sufficient conditions for an h-Shuhan matrix to be positive semi-definite, virtually positive semi-definite, or generalized positive semi-definite. Think of it as a master key that unlocks the secrets of these matrices, revealing their hidden properties.
That sounds incredibly powerful. So if we have an h-Shuhan matrix in front of us, and we want to know if it's positive definite or one of its variants, we simply refer to this theorem and check if it meets any of the listed conditions.
Exactly.
It's like having a definitive checklist.
It lays out all the possibilities in a clear and concise manner.
Okay.
For positive semi-definiteness, the theorem states that the matrix must match one of the specific matrix types introduced earlier, AN, DHN, A6, A7, or A8, and satisfy a particular inequality involving H for that specific type. It's like a recipe book, where each recipe or condition leads to a specific type of positive definiteness.
And what about the other types of positive definiteness, like virtual positive semi-definiteness and generalized positive semi-definiteness?
Yeah.
Does the theorem provide similar checklists for them?
It absolutely does.
Ah.
The theorem provides analogous sets of conditions for both virtual positive semi-definiteness and generalized positive semi-definiteness. It's like a comprehensive roadmap that guides us through the landscape of these matrices and their properties, allowing us to easily determine which type of positive definiteness, if any, they exhibit.
It's amazing how the authors managed to distill such complex concepts into this clear and concise theorem.
Yeah.
It's like they've taken this tangled web of mathematical ideas and woven them into a beautiful tapestry that reveals the underlying patterns and connections.
Indeed. It's a testament to the power of mathematical rigor and insight. But we've covered a lot of ground in this first part of our deep dive. We've explored the basic definition of h-Shuhan matrices,
Yeah.
their connection to generalized Cartan matrices, the concept of positive definiteness and its variations, and we've even gotten a glimpse of the classification theorem that awaits us.
I agree. It's been quite a journey so far. We've laid the groundwork for a deeper understanding of these fascinating mathematical objects, and I'm eager to continue exploring their intricacies in the next part of our deep dive.
I'm with you. In the next part, we'll delve further into the details of specific matrix types, unravel the logic behind the proofs, and explore the implications of the classification theorem.
Awesome.
There's still much more to uncover, so stay tuned. Welcome back to our deep dive into the world of h-Shuhan matrices. In this part, I'm excited to really get into the nitty-gritty of the proofs and see how the authors build their arguments step by step.
I'm with you. We've talked about the big picture, but now I'm eager to zoom in and really appreciate the elegance and ingenuity of their mathematical reasoning.
Absolutely. And a great place to start is with Lemma 2.1,
Okay.
which lays the groundwork for many of the subsequent proofs.
Okay.
Remember, this lemma provides a formula for calculating the determinant of a matrix that's formed by adding a scaled identity matrix to another matrix.
Yes, I recall that. It seemed like a rather technical detail at first, but I'm starting to see how it plays a crucial role in their analysis.
Precisely. Lemma 2.1 states that for any square matrix, dollar of order, none dollars, and any scalar 2, the determinant of the matrix H plus TE, where A's is the identity matrix, can be expressed as D H plus TE plus some K IN plus Tom A.
Whoa, that's quite a formula. Can you break it down for us a little bit?
Certainly. Let's unpack it piece by piece. The left-hand side, THL plus TE, represents the determinant of the matrix formed by adding 2 times the identity matrix to the matrix. On the right-hand side, we have a sum of terms. The first term, $2, is simply $2 raised to the power of naught, where naught is the order of the matrix. The remaining terms involve a double summation.
Okay, I see. So we have $2 plus a sum over $1, where cool goes from $1 to $1, but what's going on with this bind and 2?
Good question. The notation RON represents the set of all possible subsets of size dollars that can be chosen from the set $2 and dollars.
Okay.
In essence, it's telling us to consider all possible combinations of rows and columns from the original matrix, denotes the principal submatrix of dollar formed by selecting the rows and columns corresponding to the indices in the subset dollar. So for each value of dollars, we're considering all possible submatrices of size to calculating their determinants and adding them up.
Right.
Then we multiply this sum by naught raised to the power of nk. It's like we're systematically exploring all the building blocks of the matrix plus TE and combining their contributions to get the overall determinant. Precisely. And this formula, while seemingly complex, provides a powerful tool for analyzing the properties of matrices like I plus TEE. For example, in Proposition 2.2, the authors use this formula to demonstrate a crucial link between virtual positive semi-definiteness and eigenvalues.
I remember that proposition. It states that if a matrix dollars is virtually positive, semi-definite, then all its eigenvalues must be non-negative.
Yeah.
Can you walk us through how they use Lemma 2.1 to prove this?
Absolutely. The proof is quite elegant, relying on a proof by contradiction.
Okay.
Let's assume, for the sake of contradiction, that $dollars has a negative eigenvalue, say lambda, where lambda is a positive number. Now, using Lemma 2.1, we can write the determinant of the matrix H plus lambda E as lambda E as det as PPA plus lambda plus the H.
Right.
Which, okay, I see how they've applied the formula from Lemma 2.1 here.
Right.
But how does this lead to a contradiction?
Well, since we assume that lambda is an eigenvalue of dollars, this means that H plus lambda E is where the...
This is a fundamental property of eigenvalues. Adding an eigenvalue times the identity matrix to the original matrix results in a singular matrix, meaning its determinant is 0.
Oh, that makes sense.
Right.
So we have $0 lambda and plus lambda and some dollar, but where's the contradiction?
The contradiction arises from the fact that dollars is virtually positive semi-definite.
Okay.
This implies that all the determinants of its principal submatrices denoted by dollars on negative. Additionally, lambda is positive, because lambda is positive. Therefore, the right-hand side of the equation is strictly positive, while the left-hand side is 0. This is a clear contradiction, which means our initial assumption that dollars has a negative eigenvalue must be false.
That's a clever use of proof by contradiction.
Yeah.
They essentially showed that assuming a negative eigenvalue leads to an impossible scenario, forcing us to conclude that all eigenvalues of dollars must be non-negative.
Exactly.
It's like a mathematical detective eliminating all of their suspects to arrive at the truth.
It's a powerful logical technique that mathematicians use to demonstrate the validity of statements. And this particular proof beautifully illustrates how seemingly abstract concepts like determinants, eigenvalues, and virtual positive semi-definiteness are intricately linked.
It's certainly making me appreciate the elegance and rigor of mathematical reasoning.
Yeah.
But the paper doesn't just stop at exploring these general properties, does it? It also delves into specific types of matrices.
Right.
Particularly those h-Shuhan matrices with h less than 2.
You're absolutely right. Section 3 of the paper is where the authors really get into the specifics, introducing various types of h-Shuhan matrices and exploring their properties in detail.
Okay.
One particularly interesting matrix type is BHN, which is a symmetric h-Shuhan matrix with a specific pattern of h's ones and zeros.
Yes, I recall each n being a central character in their investigation. They define this concept of Dan as the largest real number that satisfies a certain equation related to h of n. It seemed like a key concept, but I'm still not entirely sure what it represents or why it's so important.
Nn is indeed crucial for understanding the behavior of Bn.
Okay.
To put it simply, n is the largest eigenvalue of the matrix n, 2h natural BHN.
Okay.
You can think of it as a threshold that determines whether Bn maintains its positive definiteness or loses it.
Gotcha.
As n approaches its upper bound, Bn gets closer to that critical point where its stability is at stake.
That's a helpful way to visualize it.
Yeah.
So finding the bounds for n is like identifying the safe zone where Bn remains positive definite. But how do they actually go about finding these bounds?
They use a combination of clever techniques.
Okay.
In Lemma 3.4, they demonstrate that n increases as n increases,
Right.
but it always remains bounded by h plus a constant approximately 2.04998. The proof relies on induction, a common technique in mathematics where you prove a statement for a base case and then show that if it holds for some n, it also holds for n plus 1.
So they're essentially establishing a chain reaction of inequalities showing that each n is greater than its predecessor, but they all remain trapped beneath this h plus constant ceiling.
Right.
It's like a staircase that keeps going up but has a roof it can't break through.
That's a great analogy. And to prove this, they meticulously analyze the structure of Bn and its determinants. They observed that the determinant of Bn can be expressed recursively in terms of the determinants of smaller matrices. This allows them to establish the inductive step and prove that n is always greater than n1.
It's like they're peeling back the layers of Bn, revealing its recursive structure and using it to derive these inequalities. But how do they establish the upper bound that n is always less than h plus the constant?
That's where Lemma 3.5 comes in, and it involves a rather ingenious approach. They introduce a new function defined as h2 plus 4 plus 4. This function plays a key role in proving the upper bound for n.
I'm seeing this function now in Lemma 3.5. It seems to involve some square roots and algebraic manipulations. How does this seemingly unrelated function help them pin down n?
It's all about clever connections and strategic substitutions. By analyzing the properties of 0, they show that it's a decreasing function for dollars less than 2.8, and that its maximum value is approximately 2.04998.
Okay.
They then cleverly relate this function to the equation that defines n and use its properties to establish that n is always strictly less than 0, and therefore less than the constant 2.04998.
It's like they found a hidden link between this abstract function and the behavior of n. It's a testament to their mathematical intuition and ability to connect seemingly disparate concepts. But I'm noticing that they also provide specific values for values of n from 2 to 8 in proposition 3.7. How did they manage to calculate these exact values, especially those involving trigonometric functions?
That's where their deep understanding of algebra and trigonometry shines through. They cleverly manipulate the equations that define n for these specific values of and utilizing trigonometric identities and relationships to find the roots. For example, for BA6 being tau be the 7 and BH8, the expressions involve trigonometric functions like cosine and inverse trigonometric functions, highlighting the intricate dance between these seemingly distinct branches of mathematics.
It's like they're wielding these mathematical tools with incredible precision, extracting these exact values from a jungle of equations. It's both impressive and inspiring to see them navigate these complex calculations with such ease.
It certainly is. And these specific values provide concrete examples of how n behaves as increases, confirming their earlier findings about its boundedness, and providing further insights into the characteristics of BH.
This has been an incredibly enlightening journey so far. We've gone from understanding the general properties of h-Shuhan matrices to delving into the specifics of BAOE and its fascinating N concept. We've even had a taste of how the authors use mathematical tools and techniques to construct their proofs and arrive at their conclusions. But I feel like we're building towards something even bigger, the grand finale of their investigation, the classification theorem.
You're absolutely right. In the next part of our deep dive, we'll explore the classification theorem in all its glory. We'll unravel its implications, delve into its applications to specific matrices, and witness how it beautifully ties together all the concepts we've explored so far.
I can't wait. It feels like we've climbed a mathematical mountain and are about to reach the summit where we'll have a breathtaking view of the entire landscape. I'm eager to see how everything connects and what insights await us. Welcome back to the deep dive. We've been on quite a journey exploring these h-Shuhan matrices, delving into their structure and properties and connections to broader areas of mathematics. I'm really excited to finally tackle the main event, the classification theorem.
Yeah, I agree. This theorem really does feel like the culmination of all our previous work, bringing together all the different pieces of the puzzle.
Exactly. So can you remind us what this classification theorem actually does? What problem does it solve?
Of course. Remember, we've been talking about different types of positive definiteness.
Right.
Positive semi-definite, virtually positive semi-definite, and generalized positive semi-definite. This classification theorem, presented as theorem 3.9 in the paper, gives us specific conditions to determine when an h-Shuhan matrix with h less than 2 falls into one of these categories.
So it's like a definitive guidebook for figuring out the positive definiteness of these special h-Shuhan matrices.
Right.
Could you walk us through what the theorem actually says?
Absolutely. Let's start with positive semi-definiteness. The theorem states that an h-Shuhan matrix POEN with 122 is positive semi-definite if and only if it can be classified as one of the following types. A 1-twed with 1 plus the h with a fev and 2 L's with POEN with p and with be a defers.
Pi with the 1, par 1 plus POEN with the 4.
That's quite a list. So essentially, if our matrix matches one of these types and its h value meets the corresponding inequality, we know it's positive semi-definite.
Precisely. It really simplifies the process of checking for positive semi-definiteness.
Yeah, no kidding.
Now, for virtual positive semi-definiteness, the theorem states that an h-Shuhan matrix 8 is 1 with 22 is virtually positive semi-definite if and only if it can be classified as one of the following types. On of 1 with onapod, on apason with 1 1 with onapod, at 1 over the 1 with anana, 8 $10 with 30 suit 4, 8 $10 with 32, and $18 with 1 with apparents with 1. Interesting. So for virtual positive semi-definiteness, the restriction on h seems to be simply that it has to be greater than or equal to 1 for most of these types.
That's right. And notice that the types listed for virtual positive semi-definiteness include all the types listed for positive semi-definiteness.
Right.
This makes sense because positive semi-definiteness implies virtual positive semi-definiteness.
So it's like a hierarchy of conditions. What about generalized positive semi-definiteness? What does the theorem tell us about that?
For generalized positive semi-definiteness, the theorem states that an h-Shuhan matrix, dollars with any 2, is generalized positive semi-definite if and only if one of the following holds. $1 is $7 is $7 plus 1, $10 all is one of the exceptional types. H is $7, M H and dollars is dollars, and 172 R's.
So for generalized positive semi-definiteness, the types on dollars are always included regardless of the value of h.
Right.
And for Chayes, we have a similar condition on h as we saw for positive semi-definiteness.
Precisely. This classification theorem provides a clear and comprehensive set of criteria to determine the positive definiteness properties of any h-Shuhan matrix with 3-to-1 matrix.
Right.
It's a powerful tool that simplifies the analysis and understanding of these matrices.
It's incredibly impressive how the authors managed to derive this comprehensive theorem. But I'm curious, did they provide any insights into why these specific matrix types and conditions appear in the theorem? Feels like there must be some deeper reasons behind these classifications.
You're right to question that. The authors do offer some explanations and insights in the subsequent remarks and propositions. For example, remark 3.8 delves into why the values of 77, 7-ness, and 19 nutties, which are crucial for understanding the behavior of certain h-Shuhan matrices, cannot be expressed using simple radical expressions.
I remember that. The paper mentions using trigonometric and inverse trigonometric functions to represent these values, but it didn't fully explain why radicals weren't sufficient. Can you elaborate on that?
Certainly. This has to do with a fascinating area of mathematics called Galois theory. In essence, Galois theory provides tools to determine whether the roots of a polynomial can be expressed using radicals operations like taking square roots, cube roots, and so on. In the case of Ni, the authors show that the polynomial associated with it has a Galois group that's too complex to allow for solutions expressible solely with radicals.
So it's not just that these values are difficult to express with radicals.
Right.
It's that it's fundamentally impossible to do so.
Yeah.
It's like trying to fit a square peg in a round hole.
Exactly. And this insight highlights the depth and complexity hidden within these seemingly simple h-Shuhan matrices. There's a whole world of abstract algebra and number theory lurking beneath the surface, influencing their properties and behavior.
It's a reminder that mathematics is full of surprises and unexpected connections.
Yeah.
But the paper doesn't just stop exploring these fascinating details about new knowledge, does it?
Well, no, it doesn't.
It also extends the concept of positive definiteness to generalized Cartan matrices, bringing us back to the world of Lie algebras.
Absolutely. The authors bridge the gap between h-Shuhan matrices and generalized Cartan matrices, showing how the properties of the former can provide insights into the latter.
Okay.
For example, Proposition 3.90 states that an h-Shu generalized Cartan matrix is virtually positive, semi-definite, if only if dull, 22.
Again, we see this emphasis on the value of H as a crucial factor in determining the properties of these matrices.
Indeed, and this connection between h-Shuhan matrices and generalized Cartan matrices highlights the power of mathematical generalization. By studying these seemingly specialized h-Shuhan matrices, the authors are able to uncover insights that apply to a broader class of mathematical objects, the generalized Cartan matrices, which have far-reaching implications in areas like Lie algebras and representation theory.
It's a testament to the beauty and interconnectedness of mathematics, how exploring seemingly niche concepts can lead to discoveries with broader significance. This deep dive has been an incredible journey. We've delved into the intricate world of h-Shuhan matrices, exploring their structure, their connection to generalized Cartan matrices, and the fascinating concept of positive definiteness and its variations. We've even uncovered hidden connections to abstract algebra and Galois theory.
I agree. It's been an incredibly rewarding exploration, and the classification theorem with its elegant conditions and surprising connections stands as a testament to the power of mathematical ingenuity and rigor.
This deep dive has definitely sparked a desire in me to learn more about these topics, to explore the references mentioned in the paper, and to see how these concepts apply to real-world problems in areas like physics and engineering.
That's the beauty of mathematics. It's a never-ending journey of discovery, full of surprising connections and fascinating applications. And this paper has provided us with a valuable map to guide us further on that journey.
Thank you for joining us on this deep dive into the world of h-Shuhan matrices. We hope you've enjoyed the journey as much as we have. Until next time, happy exploring. Welcome to the deep dive. Today we're going to be diving into h-Shuhan matrices.
Yeah, these matrices are really fascinating, especially when h is less than 2.
Okay, cool.
And we're going to be looking at their connection to generalized Cartan matrices.
Okay.
And the whole concept of positive semi-definiteness.
Awesome.
Yes.
So the paper that we're looking at today is titled Positive Determinacy of h-Shuhan matrices with h less than 2.
Yes.
And I have to say this is a pretty dense paper.
It is. It is.
But hopefully we'll be able to break it down for everybody.
Yes, definitely.
Right.
We're going to break down all those complex equations and proofs so you can really grasp those key insights
Yeah.
without getting lost in mathematical weeds.
For sure. So maybe let's just start with like the basics.
Cool.
Like what exactly are h-Shuhan matrices?
Right.
And how do they relate to these generalized Cartan matrices you mentioned?
Yeah. So you can think of h-Shuhan matrices as like a generalization of generalized Cartan matrices. And generalized Cartan matrices play a really crucial role in classifying Lie algebras,
Okay.
which are these mathematical structures
Right.
that are fundamental to understanding symmetry
Symmetry. I like it.
in both math and physics.
Okay, cool.
Yeah.
So, but how do these h-Shuhan matrices actually connect to generalized Cartan matrices?
Right.
Is there some kind of like relationship?
There is, and it's surprisingly straightforward.
Okay.
If you take an h-Shuhan matrix, you add 2 minus h times the identity matrix, and boom, you get a generalized Cartan matrix.
Okay, so it's like a pretty simple like transformation.
It is, yeah.
Okay.
And this paper that we're looking at really dives deep into the properties of these h-Shuhan matrices,
Okay.
especially their positive definiteness.
Okay, now positive definiteness is something that I remember vaguely from linear algebra.
Yes.
But can you give us like a quick refresher?
Absolutely.
Why is this property so important?
Yeah.
Especially in this context.
Positive definiteness is key.
Yeah.
It ensures stability and unique solutions. You can think of it as a guarantee that things behave nicely.
I like that.
Yeah, and this paper specifically focuses on h-Shuhan matrices where h is less than 2
Right.
and explores the conditions needed for them to be positive definite within this range.
So why less than 2?
That's a great question.
Yeah.
That's where things get really interesting.
Okay.
This range exhibits some unique behaviors that the authors explore using trigonometric functions.
Trigonometry, now that's a curveball I was not expecting.
Yeah.
So we're going from matrices to sines and cosines.
It might seem like an odd pairing.
Yeah.
But, math is full of these surprising connections.
Okay.
So think of trigonometric functions as like a special tool perfectly suited for analyzing these matrices when h is less than 2.
Okay.
They provide the right lens to see the patterns and relationships.
Gotcha. So we're using the cyclical nature of trig functions
Exactly.
to analyze the behavior of these matrices
Yeah.
within that specific range.
Exactly.
Okay, cool.
And they introduce several specific matrices, like a sub, B sub, D sub, and so on,
Okay.
whose properties, especially their determinants, can be elegantly expressed using trigonometric functions when h is less than 2.
Okay, I see. So they've identified specific matrices
Yes.
that when analyzed through this lens of trigonometry
Exactly.
can reveal a lot about the broader behavior.
Yeah.
Okay.
And they help us establish conditions for when a given h-Shuhan matrix is positive semi-definite,
Gotcha.
which in turn tells us about the corresponding generalized Cartan matrix.
Okay, so it's not just random. These matrices were carefully selected because
Yeah.
their properties,
Exactly.
when expressed using trigonometry,
Yes.
provide these valuable insights.
Yes.
Okay, cool.
For example, Proposition 3.3
Yeah.
establishes the conditions for these specific matrices to be positive semi-definite
Oh,
or
no.
virtual positive semi-definite
Go.
based on the value of h.
Okay.
So let's consider a sub.
All right.
Proposition 3.3 states that this matrix is positive semi-definite if and only if
Okay.
it's greater than or equal to 2 times the cosine of pi divided by n plus 1.
Wow. Okay, so we have a very clear and concise condition
Yes.
for positive semi-definiteness
Exactly.
derived using trigonometry.
Using trigonometry, exactly.
Okay, cool.
Yes.
So I'm seeing like a pattern here
Yes.
of establishing these clear criteria
Exactly.
for when these matrices behave nicely.
You're absolutely right.
Okay,
The
great.
paper systematically examines each of these specific matrices,
Okay.
deriving similar conditions based on h,
Okay.
using trigonometric identities and properties.
I like it.
And this brings us to another intriguing concept
Okay.
introduced in the paper,
Okay.
a special value
Okay.
denoted as sub.
Okay, so sub, what's so special about this value?
So it's defined as the largest real number,
Okay.
for which the determinant of a slightly modified version of the B sub matrix,
Okay.
which is denoted as B sub,
Uh-huh.
becomes 0.
Okay.
So this essentially gives us a critical boundary
Yes.
for understanding the behavior of B sub.
So sub is like a tipping point
Mhm.
where the determinant of this specific matrix
Yes,
flips from being positive to 0.
exactly.
Okay.
And it gives us a way to understand how the positive semi-definiteness of B sub changes
Okay.
as the matrix size represented by n increases.
Okay, cool.
So for instance, lemma 3.4 shows that E sub sub increases as n increases.
Okay.
So this reveals something fundamental about how the positive semi-definiteness of this specific matrix type evolves.
Cool. So by analyzing the specific value,
Yes.
we get like a glimpse into the inner workings of this matrix type and how its properties change with its size.
You got it.
Awesome. Okay.
And the paper goes further. It establishes an upper bound for E sub sub, a value denoted as
epsilon,
which is approximately 2.04998. And this finding implies that the largest eigenvalue of B sub 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 will always be less than H plus ALA.
Wow.
No matter how large AI gets.
Okay, so that's fascinating.
It is.
It puts like a limit on how much the eigenvalues can grow for this specific matrix.
For this specific matrix type.
Okay.
Precisely.
Awesome.
These findings about E sub sub and its upper bound ultimately contribute to a deeper understanding of the conditions for positive semi-definiteness in the specific matrix type.
Wow, this is really incredible. We're finding these elegant relationships.
I know.
And boundaries.
Yes.
Even in this abstract world of matrices.
It speaks to the underlying order and beauty of mathematics, doesn't it?
It really does. It's like these matrices are revealing these hidden patterns and relationships that we're uncovering.
Absolutely. And this is just the beginning.
Oh, no.
The next section of the paper takes us into a complete classification of h-Shuhan matrices.
Okay.
Based on their positive semi-definiteness.
Which is where things get really exciting.
That sounds like a perfect stopping point for part of our deep dive.
It does.
We've laid the groundwork.
Yes.
By defining these key concepts.
Yes.
And exploring some of these like foundational propositions.
We've established the importance of positive definiteness.
Yeah.
Introduced those intriguing trigonometric connections.
Yes.
And even delved into the behavior of specific matrices.
Like B sub 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 sub.
Like B sub sub sub.
Awesome.
Yes.
So join us for part 2, where we'll unpack that classification system.
Yes.
And explore the broader implications of these findings.
Can't wait.
Me too. This is really cool.
It is.
I like this paper a lot.
Me too.
Okay, cool. Welcome back to the deep dive. We're picking up where we left off, exploring the fascinating world of h-Shuhan matrices.
Yes. Last time we established those foundational concepts.
Right.
And we really explored that connection between these matrices, positive definiteness, and even trigonometry.
Yeah, it was a lot of fun.
It was a good time.
And now we're ready to tackle one of the highlights of this paper.
Yes.
This comprehensive classification system for h-Shuhan matrices.
It's like assembling this complex puzzle.
Okay.
And this classification theorem is the key to seeing the complete picture.
I like that. So let's dive into this theorem. What does it actually tell us?
So the theorem we're talking about is theorem 3.9.
Okay.
And it provides a complete classification of positive semi-definite, virtual positive semi-definite, and generalized positive semi-definite h-Shuhan matrices for when H is less than 2.
Okay.
It's like a roadmap guiding us through this diverse landscape of these matrices.
Okay, a roadmap. I got an analogy.
Yeah.
So how does this classification actually work?
Right.
What are the different categories and how are they defined?
So the theorem breaks down the classification into 3 main parts.
Okay.
First, we have positive semi-definite matrices. So this part tells us that an h-Shuhan matrix is positive semi-definite if and only if it, or a matrix we get by rearranging its rows and columns, belongs to one of 5 specific types.
Okay, what are those?
So we've got A sub 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 sub, D sub 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 sub, E sub 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 6 sub, E sub 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 7 sub, or E sub 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 8 sub.
Okay.
And for each type, there's a specific condition on the value of H that needs to be met.
Right. So it's not just about having the right matrix structure.
Exactly.
The value of H also plays a crucial role.
Exactly. Both the structure and the value of H are critical.
It's like a delicate balancing act.
It is.
Between form and numerical value.
Yeah, I like that.
Okay, so what about the other 2 categories?
Okay, so the second part of the theorem deals with virtual positive semi-definite matrices.
Okay.
This category includes all those positive semi-definite matrices we just discussed.
Okay.
But it also includes matrices that belong to 3 additional types.
Okay.
So B sub 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 sub, F sub 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 4 sub, and G sub 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 2 sub.
Gotcha. So this category is like an expanded version of the first one.
Precisely.
Okay, encompassing a wider range of matrices.
Exactly. And it relaxes the strict requirements of positive semi-definiteness
Okay,
while still maintaining some desirable properties.
gotcha. And what about the third and final category?
Right. So the third part focuses on generalized positive semi-definite matrices.
Okay.
This category, like the second, includes all those positive semi-definite matrices we talked about. However, the condition for B sub is slightly different here.
Okay, how's it?
It needs to satisfy Horsch being greater than or equal to that special value, the sub we discussed earlier.
Ah, so that a sub value comes back into play.
It does. It ties everything together.
It really does. This classification system is incredibly comprehensive.
Yes.
But why is it so important?
Right.
What kind of insights does it offer beyond simply categorizing these matrices?
That's a key question.
Yeah.
This classification is a game changer because it gives us a way to predict the behavior of h-Shuhan matrices
Okay.
without having to go through tons of tedious calculations.
Right.
Just by knowing the type of matrix and the value of H, we can immediately determine if it's positive semi-definite, virtual positive semi-definite, or generalized positive semi-definite.
Okay.
And this knowledge has ripple effects impacting our understanding of the corresponding generalized Cartan matrices,
Right.
which ultimately shape our understanding of Lie algebras.
So it's like a cheat sheet for understanding these complex mathematical objects.
Exactly. We can bypass a lot of heavy lifting thanks to this classification.
Right. And it really highlights the power of finding these elegant patterns and relationships in mathematics.
It does.
And speaking of connections, the paper doesn't stop there.
It does not.
It goes on to explore affine generalized Cartan matrices
Yes.
and their connection to Crucian matrices.
Right. Affine generalized Cartan matrices are fascinating.
They sound it.
They're essentially a special type of generalized Cartan matrix that pops up when we're studying infinite dimensional Lie algebras.
Whoa, infinite dimensional Lie algebra.
A whole other deep dive waiting to happen.
That sounds awesome.
It does.
Okay, so how do these affine generalized Cartan matrices connect to the h-Shuhan matrices we've been focusing on?
So the paper introduces a notation,
Okay.
to bridge the gap.
Okay.
So if S is an affine generalized Cartan matrix,
Okay.
then sub represents the corresponding h-Shuhan matrix
Okay.
we get by adding H minus 2 times the identity matrix to S.
Okay, so it's like a similar transformation to what we talked about before.
Exactly.
Adding a multiple of the identity matrix.
Yes.
But now applied to these affine generalized Cartan matrices.
Exactly. And the paper delves into the conditions under which this transformed matrix sub
Okay.
is virtual positive semi-definite.
Okay.
Proposition 3.10z states that sub is virtual positive semi-definite
Okay.
if and only if H is greater than or equal to 2.
So it seems like the value of H continues to be a critical factor.
It really does.
Even when we shift to these affine generalized Cartan matrices.
Absolutely. And the paper goes on to explore specific matrices derived from affine generalized Cartan matrices.
Okay.
Looking into the conditions for their generalized positive semi-definiteness.
Okay.
Propositions 3.11 and 3.13, for example,
Okay.
examine specific matrices like H sub 1, sub 2 sub, F sub and up sub 4 sub, B sub and others, outlining when they exhibit this property based on the value of H.
Okay, cool. It's impressive how the authors systematically build this framework for understanding
It is.
positive semi-definiteness in both regular and affine generalized Cartan matrices,
Right.
all through this lens of h-Shuhan matrices.
It's a testament to the power of mathematical abstraction.
Right.
By finding these connections, we gain a deeper understanding of seemingly disparate areas.
Yeah, and just when you think it can't get any better, the paper brings us full circle.
It does.
It concludes by revisiting generalized Cartan matrices and provides a final classification
Exactly.
based on their types.
Right. This is where proposition 3.15 comes in.
Yeah, okay.
It essentially categorizes generalized positive semi-definite and generalized positive definite generalized Cartan matrices based on their specific types.
Okay, so after this journey through h-Shuhan matrices, we're back to familiar territory.
We are.
But now with a richer understanding
right.
of generalized Cartan matrices.
We've explored the conditions for their positive definiteness in both finite and affine cases.
Right.
And proposition 3.15 tells us that finite types like a sub 2 and sub, D sub 2 sub, E sub 6 sub, E sub 7 sub, and E sub 8 sub are generalized positive definite.
It feels like we've climbed a mathematical mountain.
I know, right?
And now we have this incredible view from the top.
It's beautiful up here.
It is. Welcome back to the deep dive. We spent the last two parts exploring h-Shuhan matrices,
Yes, a lot of fun.
their connection to generalized Cartan matrices,
You're right.
and even delved into that classification system based on their positive semi-definiteness.
Yes, it's been a really interesting journey.
It has. It's been a whirlwind of mathematical insights,
Absolutely.
and I'm eager to keep going.
Okay.
You mentioned diving into some of the proofs behind these key findings.
Yes,
And I think that's a fantastic way to wrap up our deep dive.
absolutely. Proofs are the backbone of mathematics, Right. And understanding them gives us a deeper appreciation for the logical structure and the interconnectedness of these concepts.
For sure. So where should we start? Which proofs offer the most revealing insights?
Okay, let's start with proposition 2.2.
Okay.
Which establishes that the eigenvalues of a virtual positive semi-definite matrix are always non-negative.
Okay.
It's a foundational result that underpins many of the subsequent findings in the paper.
Okay, so proposition 2.2, it states that if a matrix, let's call H,
Right.
is virtual positive semi-definite,
Yes.
then all of its eigenvalues are greater than or equal to 0.
Exactly.
How do the authors go about proving this?
So the proof relies on a clever technique called proof by contradiction.
Okay, I like it already.
So they start by assuming that there's an eigenvalue, let's call it yes, which is less than 0.
Okay.
This means that the determinant of the matrix, HAE, where E is the identity matrix, would have to be 0.
Right, because if lambda is an eigenvalue, then HAE has to be a singular matrix, meaning its determinant is 0.
Exactly.
So how does this lead to a contradiction?
So they use the fact that H is virtual positive semi-definite,
Okay.
which means all of its principal minors are non-negative.
Right, we discussed those earlier.
Yes.
The determinants of those submatrices you get by removing some rows and columns.
Precisely.
So we have a matrix H with non-negative principal minors,
Yes.
and we're assuming it has this negative eigenvalue lambda.
Right.
Where do we go from there?
Okay, so this is where things get interesting.
Okay.
They use lemma 2.1,
Okay.
which gives us a way to express the determinant of H plus E
Okay.
in terms of the determinant of H and the determinants of its principal minors.
So lemma 2.1 gives us a tool to deconstruct
Yes.
the determinant of this modified matrix.
Exactly. And because we know all the principal minors of H are non-negative, and lambda is positive since we assumed a negative eigenvalue, and are now looking at its negative.
Right.
That expression for the determinant of H plus EE from lemma 2.1 becomes a sum of non-negative terms plus a positive term, sum sub.
So we're guaranteed to get a positive value for the determinant of H plus E.
Precisely.
Okay.
But this contradicts our initial assumption that lambda is a negative eigenvalue.
Right.
Because that would make the determinant of HE 0.
Right.
So our initial assumption must be wrong.
Okay.
Meaning all eigenvalues of H have to be non-negative.
That's a really elegant way to prove it, using that assumption against itself
It
to
is.
show why it can't be true. It's amazing how these seemingly disparate concepts,
I know.
eigenvalues, determinants, principal minors,
Yes.
all come together to lead to this conclusion.
It highlights the power of mathematical reasoning.
Right?
And how these different ideas are interconnected in fascinating ways.
For sure, for sure. Okay, let's shift gears a little bit
Oh.
and look at the proof for proposition 2.4,
Okay.
which connects virtual positive semi-definiteness to those generalized Cartan matrices
Yes.
of finite type.
Right.
So proposition 2.4 was a key part of our discussion earlier.
It was.
It states that if H is less than 2,
Mm-hmm.
and H is a virtual positive semi-definite h-Shuhan matrix,
Right.
then adding 2H times the identity matrix to H
Yes.
gives us a generalized Cartan matrix of finite type.
That's right.
How do they go about proving this
Okay.
connection?
So the proof revolves around that fundamental relationship between h-Shuhan matrices and generalized Cartan matrices.
Right.
Remember, an h-Shuhan matrix, H plus 2H times the identity matrix E, results in a generalized Cartan matrix.
Right. That connection is central to the whole paper.
It is.
So how do we go from knowing that H is virtual positive semi-definite
Okay.
to proving that the resulting generalized Cartan matrix is of finite type?
Okay, so they cleverly utilize a crucial result from generalized Cartan matrix theory. A generalized Cartan matrix is of finite type if and only if it's positive definite. So the goal becomes demonstrating that the resulting generalized Cartan matrix H plus 2HE
Right.
is positive definite.
So the focus shifts to proving that this modified matrix
Yes.
has that positive definiteness property.
Exactly. And they achieve this by using what we know about virtual positive semi-definite matrices.
Okay.
Since H is virtual positive semi-definite,
Right.
and 2H is positive because H is less than 2.
Right.
Proposition 2.4 tells us that H plus 2HE is virtual positive definite.
Okay.
Then according to Proposition 1.4, this means H plus 2HE, our generalized Cartan matrix,
Yeah.
has to be positive definite.
It's like a domino effect.
Yeah.
We establish one property and then use it to deduce another.
Exactly.
These proofs really highlight the logical framework that underpins all these seemingly abstract mathematical concepts.
It's like we're peeling back the layers of an onion,
Yeah.
revealing this intricate structure and connections within.
I had to say, this deep dive into the world of h-Shuhan matrices has been incredibly rewarding.
It has.
We've gone from basic definitions to exploring complex theorems and even delved into the proofs that form the foundation of these findings.
Absolutely. And through it all, we've seen how these seemingly abstract concepts connect to broader ideas in mathematics and physics,
Right.
showcasing the beauty and interconnectedness of this field.
For our listeners who are eager to explore further,
Yes.
I highly recommend diving into the original paper.
Yes.
We've only scratched the surface here,
We have.
and there's a wealth of additional insights waiting to be discovered.
Absolutely. The world of mathematics is vast and full of wonders.
It is.
And I encourage everyone to keep exploring, keep questioning, and keep diving deep.
That's the perfect note to end on. Thank you for joining us on this mathematical journey. Until next time, keep those minds curious and keep diving deep into the fascinating world of knowledge. Welcome to the Deep Dive. Today, we're diving into some really fascinating mathematical concepts. We're going to be exploring the world of h-Shuhan matrices and their connection to generalized Cartan matrices, and this whole concept of positive semi-definiteness.
That's going to be exciting.
Yeah, it sounds a little complex, but I think with your help, we can break it down.
Absolutely. I think we can definitely unpack it and make it accessible. These h-Shuhan matrices, they might sound a little intimidating at first, but they're really elegant tools that can help us kind of unlock insights into the structure of other mathematical structures, particularly Lie algebras, which, have really cool applications in physics, cryptography, economics, you name it.
So before we jump into all of that, can we maybe just start with the basics? What exactly is an h-Shuhan matrix?
Right. So imagine you have a square matrix.
Okay.
Your rows and columns of numbers, and in an h-Shuhan matrix, all of the elements along the main diagonal, so top left to bottom right, are equal to a specific real number, which we'll call h. And so that's where the name comes from, h-Shuhan.
Okay. So h is kind of the defining characteristic of this type of matrix.
Exactly.
Okay. What else? What else makes it special?
So all the elements that aren't on that main diagonal, we call those the off-diagonal elements, have to be integers, specifically non-positive integers, so less than or equal to 0.
Got it. Okay. So we've got our value h running down the diagonal. All the other entries are non-positive integers. Is there a third condition that completes the definition?
Yeah. So the third condition says that for any pair of off-diagonal elements that are in symmetrical positions, so if you think about flipping the matrix along that main diagonal, they're mirror images of each other.
I see. Okay.
They either have to be equal or one is strictly less than the other, and in that case, the larger one must be -1.
Okay. So there's like a balance, like a relationship that's enforced between those off-diagonal pairs.
I see.
I'm starting to see the structure emerge here. So why are these h-Shuhan matrices so important? What can they actually tell us?
So that's where things get really exciting. It turns out that they're very intimately connected to generalized Cartan matrices.
Okay.
And Cartan matrices are really fundamental in the study of Lie algebras.
Oh, Lie algebras. Yeah, I think I've heard of those. Are those used in physics a lot?
Exactly. So they're used to describe symmetries in physical systems, but their application goes way beyond physics to cryptography, economics, even certain areas of computer science. Now, the fascinating part is that you can get from an h-Shuhan matrix to a generalized Cartan matrix through a simple transformation. You just add 2 minus h times the identity matrix, so that's the matrix with ones down the diagonal and zeros everywhere else, to the h-Shuhan matrix.
Okay, so by adding this 2 minus h times the identity matrix, we're turning our h-Shuhan matrix into a generalized Cartan matrix.
Precisely.
So then opens up all of these other applications and areas of study. It's like a hidden doorway between these mathematical concepts.
Precisely. And this deep dive that we're on today is all about understanding a crucial property that helps us classify and understand these matrices, positive semi-definiteness.
Ah, yes, positive semi-definiteness. I have to say, this whole concept of like a positive matrix has always intrigued me. So what exactly makes a matrix positive in this context?
Okay, so at the simplest level, a matrix is considered positive definite if when you multiply it by a non-zero vector and that vector's transpose, the result you get is always a positive number.
So no matter what vector you kind of throw at this matrix, it'll always spit back out a positive number.
Well, after a specific type of multiplication.
Right, right. Okay, so I think I'm starting to see that. But you mentioned something about different types of positive semi-definiteness.
Yeah, so the paper that we're looking at actually talks about three types: virtual positive semi-definite, generalized positive semi-definite, and good old-fashioned positive semi-definite.
Okay, so there's a lot more to this than meets the eye at first. I'm ready to unpack those definitions. What makes each one of these types unique?
Okay, so let's start with virtual positive semi-definite. This property has to do with the determinants of all of the submatrices you can create from the original matrix.
Hold on. Submatrices. Now, can you just remind me real quick what a submatrix is?
Yeah, so a submatrix is basically a smaller matrix that sits inside the larger matrix. You get it by like deleting some of the rows and columns of the original matrix.
Oh, okay. So it's like taking a section of the bigger matrix.
Exactly. So for virtual positive semi-definiteness, if the determinants of all of those submatrices are greater than or equal to 0, then the original matrix is called virtual positive semi-definite.
Okay. So we're looking at all the little matrices and making sure that they're all positive.
Yeah.
Okay. I think I got that. What about generalized positive semi-definite? What does that mean?
So generalized positive semi-definite has to do with the particular calculation. So you take the matrix, you multiply it by a non-zero vector and its transpose, and if that result is greater than or equal to 0, no matter what vector you choose, then we say it's generalized positive semi-definite.
Okay. So it's kind of similar to the positive definite idea, but instead of always having to be positive, it can also be 0.
That's a good way to think about it.
Okay. So are these different types of positive semi-definiteness, are they totally separate, or are there connections between them?
There are definitely connections. For instance, the paper actually shows that if a matrix is generalized positive semi-definite, then it is automatically also virtual positive semi-definite.
Okay. So there's some hierarchy here.
Yeah.
Generalized positive semi-definite is a kind of stronger condition than virtual positive semi-definite.
Yeah, you could think about it like that.
Okay. Now, you said there's a third type, just regular positive semi-definite. Where does that one fit in?
So positive semi-definite is like a special case. It occurs when a matrix is both generalized, positive semi-definite, and symmetrical.
Okay.
And remember, h-Shuhan matrices have those conditions on their off-diagonal elements, but those conditions don't necessarily mean that the matrix is symmetrical. So if an h-Shuhan matrix does happen to be symmetrical and meets the criteria for positive semi-definite, then it's just called positive semi-definite.
Okay. Okay. I think I'm starting to grasp these different definitions. So we're using these properties of the matrices, these values that they produce, the inherent structures, and we can use that to classify them into these different categories. But I'm still feeling a little bit abstract. Can we maybe look at an example just to see how all of this plays out in practice?
Sure. The paper gives a really nice example. Let's consider this 2 by 3 matrix. So the first row is 2, -7, 2. And the second row is -1, 2, 0. Now, this matrix actually doesn't strictly qualify as an h-Shuhan matrix. The off-diagonal elements in the second row don't meet that requirement of being equal or having the larger one be -1, but it still illustrates the difference between generalized positive semi-definite and virtual positive semi-definite very nicely.
Okay, so what can we learn from looking at this example?
Well, first of all, if you calculate the determinants of all the possible submatrices, which in this case include the individual entries because it's a small matrix, we find that they're all non-negative.
Okay.
So that means this matrix is virtual positive semi-definite.
So it passes the virtual positive semi-definite test.
Exactly. But if you take a vector, let's say 1, 1, and you perform that multiplication with the matrix and its transpose, you will get a negative result. So that means it fails the generalized positive semi-definite test.
Okay, so this matrix, it's virtual positive, semi-definite, but it's not generalized positive semi-definite. So it's a good example of how these concepts are distinct.
Exactly. It's a really nice counterexample.
Okay, I'm starting to appreciate all the nuance here. It's more than just saying a matrix is positive. There are these different ways to categorize them with increasing kind of precision.
Precisely.
Okay, and I'm assuming these concepts are not just theoretical. Do they have some real-world significance?
Absolutely. So imagine you're an engineer and you're designing a structure, a bridge or a skyscraper, and you want to make sure that it's stable and can withstand various loads and stresses. The forces acting on that structure, you can actually represent them with a matrix.
Okay.
And the stability of the structure can be analyzed by looking at the positive definiteness of that matrix. If it's positive definite, then you know that the structure is inherently stable.
Wow. So we can actually use these properties of matrices to assess the stability of real-world structures.
Yeah, absolutely. They provide a mathematical language for us to understand and analyze these complex physical phenomena.
I see. Okay, that's really cool. But let's bring it back to these h-Shuhan matrices and their relationship to generalized Cartan matrices. Now, I noticed the paper uses some specific notation, and and they introduce some recursive formulas to calculate certain values. Can you help me kind of decode all of that?
Sure. So remember how we talked about adding 2 minus h times the identity matrix to an h-Shuhan matrix, and that transforms it into a generalized Cartan matrix?
Go ahead.
Well, the paper uses S to represent a generalized Cartan matrix, and then ish with the H subscript is specifically the h-Shuhan matrix associated with that generalized Cartan matrix.
Okay, so that's our shorthand for the h-Shuhan matrix that goes with a specific generalized Cartan matrix.
Exactly.
Got it. What about she's and u?
So both of those have to do with determinants. So Shuba represents the determinant of the Shuhan matrix, Shu, and U represents the determinant of a slightly modified version of Shash, where you essentially add H to a specific element of Shash,
Which
an
element?
element in the first row and first column, and then you calculate the determinant of that matrix.
Okay. So we're focusing on the determinants of the Shuhan matrix and this slightly altered version. But why are determinants so important here? What do they tell us?
So determinants, they're very powerful tools in linear algebra. They can tell us whether or not a matrix is invertible. That means whether you can kind of undo its effect. And they can also tell us about whether a system of equations that's represented by the matrix has a unique solution.
Okay. So by calculating Shar and U, we're getting a deeper understanding of the way this matrix behaves and the systems it might be representing.
Exactly.
Okay. Now, what about those recursive formulas you mentioned? They look a little bit intimidating at first glance.
Yeah. So the paper introduces these notations like on, BHN, DHN, and AAJ. And each of these is defined by a recursive formula. So, for example, on is calculated as h times on minus 1 minus on minus 2. Where is that familiar value from our h-Shuhan matrix?
So we start with some initial values, and then we can use these formulas to calculate the next value in the sequence,
Yeah.
and then the next, and so on and so forth.
Exactly.
But what do these sequences actually represent in relation to the h-Shuhan matrices?
So these sequences are actually a tool to help us understand the positive definiteness of h-Shuhan matrices. So by looking at how these sequences behave, how their values change as h varies, we can figure out the conditions under which different types of h-Shuhan matrices become positive semi-definite, virtual positive semi-definite, generalized positive semi-definite.
Sounds like we're using these sequences to kind of probe the positivity of these matrices.
Exactly. It's a very clever technique.
Okay. I think this is all starting to come together. We've defined what h-Shuhan matrices are. We've explored those different types of positive semi-definiteness. We've even kind of decoded some of the key notation the paper uses. So I feel like we're building a really solid foundation here for understanding these really complex concepts.
Exactly. And now the paper takes us deeper into the world of h-Shuhan matrices, and it starts to explore some specific propositions, lemmas, that connect them to the classification of generalized Cartan matrices.
Okay.
So are you ready to dive in?
I think so. Lead the way. I'm ready to explore those deeper connections.
Okay, so let's start with proposition 2.4.
Okay.
This proposition directly links the virtual positive semi-definiteness of a generalized Cartan matrix to whether it's classified as finite or affine type.
Okay, right. Now, I think we talked about finite and affine types briefly earlier.
Yeah.
But can you just remind me, what exactly do those terms mean? And why are they important when we're talking about generalized Cartan matrices?
Sure. So in the world of Lie algebras, which these generalized Cartan matrices are closely tied to, finite type refers to Lie algebras that have a finite dimensional representation. They're kind of the well-studied, nice-behaving ones. And then affine type refers to Lie algebras that are infinite dimensional. They have a more complex structure, and they have really interesting applications in areas like string theory and quantum field theory.
Okay, so finite type is kind of like the well-behaved sibling, and
Yeah.
affine type is like the more adventurous one with its infinite dimensions and all.
Yeah, that's a fun way to think about it. So Proposition 2.4 basically says that if a generalized Cartan matrix is virtual positive semi-definite, then it must be of either finite or affine type.
Okay.
And the reverse is also true. If it's finite or affine, then it's guaranteed to be virtual positive semi-definite.
Okay, so virtual positive semi-definiteness, it acts as a filter. If it passes the test, then it goes in one of these important categories, either finite or affine type.
Exactly. And the proposition doesn't stop there. It also says that if you take a virtual positive semi-definite matrix and you add a positive multiple of the identity matrix, we'll call that lambda E, then the resulting matrix is guaranteed to be virtual positive definite.
Wait a minute, virtual positive definite. Now, is that different from virtual positive semi-definite?
Yeah. It's a subtle but important difference. So remember, for virtual positive semi-definite, all of those submatrix determinants, they have to be greater than or equal to 0. For virtual positive definite, we tighten those requirements. They all have to be strictly greater than 0, so no zeros allowed.
Okay, so we're raising the bar for virtual positive definite.
Exactly.
Okay, but why is this adding the lambda E, why is that so crucial? What does adding a positive multiple of the identity matrix do to the matrix?
So you can think of it as giving the matrix a little boost. Adding that positive multiple of the identity matrix basically shifts all of the eigenvalues, those special values associated with the matrix, in a positive direction. And remember, eigenvalues are all about how a matrix transforms vectors.
Right.
So it's like its signature.
Okay, so it's not just randomly adding, we're specifically modifying the matrix to ensure that those submatrix determinants all become strictly positive. It's like a fine-tuning process.
Exactly.
Okay.
And this leads to a really interesting observation about h-Shuhan matrices. So when h is less than 2, and our h-Shuhan matrix, let's call it H, is virtual positive semi-definite, then adding 2 minus h times the identity matrix to it, so that transformation that we talked about that turns it into a generalized Cartan matrix results in a matrix of finite type.
Oh, okay. So when h is less than 2, our virtual positive semi-definite h-Shuhan matrix is just kind of a hop, skip, and a jump away from being classified as finite type.
Exactly. It just needs that little extra push.
Okay.
Yeah.
I'm starting to see the beauty here, the connections between these different types of matrices and their properties.
Yeah. It's remarkable. And the paper continues to build on these ideas. It dives deeper into the world of h-Shuhan matrices where h is less than 2. And this section is packed with lemmas and propositions that help us understand the positive definiteness of different types of h-Shuhan matrices based on the specific values of h.
All right. Lead the way. I'm ready to explore those lemmas and propositions.
Yeah.
What's the first step on this deeper dive?
Okay, so our first stop is lemma 3.2.
Okay.
This lemma introduces some really elegant trigonometric representations for those sequences we talked about earlier on BHN and DHN, specifically when 0 is less than or equal to h, which is less than 2.
Okay. Trigonometry. Now, why does trigonometry suddenly come into play when we're talking about sequences and matrices?
Yeah, it might seem a little surprising, but trigonometry actually has a really close relationship with sequences and recursive relationships. So remember how those sequences were defined recursively, each term depending on the previous ones?
Yeah.
Well, trig functions like sine and cosine, they also exhibit very similar recursive patterns.
Okay, I see. So by using these trigonometric representations, we can take these sequences, connect them to these familiar trigonometric functions, and then maybe get some new insights into how they behave.
Exactly. And that's precisely what lemma 3.2 does. It gives us these nice trigonometric formulas for on, BHN, and DHN. So on can be represented as sine of n plus 1 times theta divided by sine of theta. BHN can be represented as 2 times cosine of n theta, and DHN is 4 times cosine of theta times cosine of n minus 1 times theta.
Okay.
And the key here is that theta is an angle that's directly related to our h value. So cosine of theta is equal to h over 2.
Okay, so knowing h, we can calculate theta, plug it into these trigonometric formulas, and bam, we have a new way to represent and understand these sequences.
Exactly. And the beauty of using trig functions is that we know a lot about how they behave. You know, they have well-defined ranges, periods, patterns of positive and negative values.
Right.
And by connecting on BHN, DHN to these trig functions, we can use that knowledge to figure out, okay, when are these sequences positive? When are they negative? When are they zero?
So it's like we've taken these abstract sequences, and now we can kind of visualize them as these waves.
Yeah.
We can see when they're above the x-axis, they're positive,
Yeah.
below the x-axis, they're negative.
Exactly.
And it all depends on the value of h and its corresponding angle, theta.
Yeah.
That's really clever.
Yeah. And the second part of Lemma 3.2 takes this even further, and it actually gives us specific conditions on the h value that will determine when each of those sequences on BHN and DHN are greater than or equal to 0.
Okay. Can you walk me through those conditions? I'm curious to see how they connect back to those trigonometric representations.
Sure. So for on to be greater than or equal to 0, h has to be greater than or equal to 2 times cosine of pi over n plus 1.
Okay.
For BHN to be greater than or equal to 0, h has to be greater than or equal to 2 times cosine of pi over 2n. And for DHN to be greater than or equal to 0, h has to be greater than or equal to 2 times cosine of pi over 2 times n minus 1.
Okay. So we have a specific threshold for h for each sequence, and it directly relates to these angles involving pi and the size of the matrix.
Exactly. Yeah. It's a delicate balance.
Okay. And these sequences, there are tools for understanding the positive definiteness of h-Shuhan matrices.
Right.
So knowing when they're positive or at least not negative, it's really crucial to help us classify these matrices.
Precisely.
This is so cool. We're uncovering all of these hidden connections between matrices and sequences and even trigonometry.
It is, yeah.
It's amazing how it all fits together.
Yeah, and the paper uses Lemma 3.2 to prove proposition 3.3,
Okay.
which goes into some specific conditions for the positive semi-definiteness of different types of h-Shuhan matrices. So these types are AN, BHN, DHN, A6, A7, A8, FH4, and GH2.
Okay, so now we're getting into some specific types of h-Shuhan matrices. Can you give me a sense of what these different types, what they look like, what their structure is, and why they're important enough to have their own labels?
Sure. So each of those represents a particular structure or pattern within the broader family of h-Shuhan matrices.
Okay.
So, for example, AN, that represents a specific type of h-Shuhan matrix with dimensions n by n.
Okay.
And then BHN represents a different structure, also of size n by n.
Okay, so we're categorizing them based on their size and the arrangement of the elements within them.
Precisely.
Okay, but why are we so interested in these particular types? What makes them special?
So a lot of these specific types, they show up in various applications of Lie algebras and also in other areas of mathematics.
Okay.
And so by understanding when they are positive semi-definite, we gain valuable insights into the behavior of the systems that they represent.
Okay, I see. So how does proposition 3.3 help us with that understanding?
So proposition 3.3, it connects the positive semi-definiteness of each of these matrix types to specific conditions on H.
Okay.
That familiar value we've been talking about.
Right.
So for instance, it states that AN is positive semi-definite if and only if H is greater than or equal to 2 times cosine of pi over n plus 1.
Wait a minute, that sounds familiar. Wasn't that the same condition from Lemma 3.2 for on to be greater than or equal to 0?
Yeah. That's exactly right. And that's the beauty of how this paper connects the dots. The positive semi-definiteness of AN is directly linked to the behavior of that on sequence.
So it's like we've solved two puzzles at once here.
Yeah.
By understanding those sequences and their connection to OS, we've also figured out how to determine the positive semi-definiteness of a specific h-Shuhan matrix. That's so elegant.
Exactly. Yeah, it's all beautifully interconnected. And proposition 3.3 provides similar conditions for each of the other matrix types. So for instance, BHN is positive semi-definite if and only if is greater than or equal to 2 times cosine of pi over 2n, which if you recall is exactly the condition we got for the BHN sequence to be non-negative.
Okay, so there's a pattern here. Each matrix type has a corresponding sequence. And the positive semi-definiteness of that matrix, it hinges on when that sequence becomes non-negative.
Yeah.
It's like each sequence is holding the key to a specific matrix type.
Yeah, exactly. That connection between those matrix types and those special sequences is central to this paper.
Okay. I'm loving this. We're unraveling these hidden connections, and it's clear that there's a lot more to positive matrices than meets the eye. There's a whole world of structure and relationships there.
Precisely.
Okay, where do we go from here?
So the next part of the paper takes us into the world of eigenvalues. Specifically, it explores the largest eigenvalue of a particular type of matrix called B hat 0n, and this eigenvalue, which will be called mu n, plays a crucial role in understanding the positive definiteness of h-Shuhan matrices of type BHN.
Okay, eigenvalues. Now, eigenvalues are those essential concepts in linear algebra. They tell us something about how a matrix transforms vectors.
Right.
Can you just give me a quick recap of why they're so important?
Sure. So think of eigenvalues as a matrix fingerprint. They give you fundamental information about how a matrix stretches or shrinks or rotates vectors.
Oh.
And the largest eigenvalue in particular often dominates the matrix's behavior. It tells you the maximum factor by which a vector can be stretched when multiplied by that matrix.
So the largest eigenvalue is like the boss of the eigenvalues. It's the one that has the most influence on how the matrix acts.
That's a good analogy. So when we're talking about h-Shuhan matrices of type BHN, the paper focuses on this largest eigenvalue of a slightly modified version of BHN, which is called B hat 0n. And this modification just involves setting h to 0, which explains the 0 subscript.
Okay, so we're taking BHN, we're setting h to 0, and then we're looking at the largest eigenvalue of that modified matrix.
Exactly.
Okay. But why are we so interested in this particular eigenvalue? What does it reveal about BHN?
So that's where it gets really interesting. The paper introduces two lemmas, lemma 3.4 and lemma 3.5, that shed light on how mud n, that largest eigenvalue of B hat 0n, behaves.
Okay, I'm all ears. What secrets do these lemmas reveal?
Okay, so lemma 3.4 tells us that mun increases as n increases, and remember, n is the size of our BHN matrix.
Right.
So as the matrix grows larger, this largest eigenvalue of its h equals 0 version, it also gets bigger.
So there's a direct relationship there. Bigger matrix, bigger eigenvalue.
Yeah, exactly.
Okay, what about lemma 3.5? What does that tell us?
So lemma 3.5 introduces a new character, a constant called epsilon, which is approximately equal to 2.04998.
Okay.
And this lemma states that as mun increases with n, it always stays bounded above by this constant epsilon. So no matter how large the matrix grows, mun n never gets bigger than epsilon.
So even though the matrix can keep expanding, this largest eigenvalue, it's trapped.
Yeah.
It hits a ceiling at this epsilon value.
Right. It highlights an inherent limit on the growth of mun, despite the potential for the matrix to become infinitely large.
So what is this epsilon? Is it just a random number? Or does it have a deeper meaning?
No, it's not random at all. The paper actually gives you a formula for calculating epsilon. It's a bit complex. It involves cube roots and some trigonometric functions, but essentially it's a very specific value that emerges from analyzing the behavior of mun.
Okay, so epsilon it's not just some arbitrary value. It's a key player in this whole mathematical game.
Yeah, exactly. And then the paper uses those two lemmas, lemma 3.4 and lemma 3.5, to prove corollary 3.6. Which states that when h is greater than or equal to epsilon, then the matrix BHN is generalized positive definite for any n greater than or equal to 2.
Wow, okay. So we've connected the value of h to the generalized positive definiteness of BHN through this special constant epsilon.
Yeah.
Why is this corollary so important?
So remember, understanding the positive definiteness of these matrices is really crucial for classifying them and understanding the systems that they describe.
Right.
So corollary 3.6 basically gives us a shortcut. If we know that h is greater than or equal to epsilon, then we automatically know that BHN is generalized positive definite. We don't have to go through all these calculations, check all the submatrices and all that stuff.
Okay, so it's like a golden ticket. If h meets this criteria, then we can skip all those complex calculations and just jump straight to the conclusion. Okay. Okay, this is great. I love how this paper is building upon itself. You know, we're connecting all these seemingly separate concepts and we're using them to unlock deeper insights. It's like watching a really well-crafted story unfold.
I agree. It's beautiful. And speaking of masterful craftsmanship, we're about to encounter one of the most significant results of this whole paper, Theorem 3.9.
Right.
Which is a central theorem that classifies h-Shuhan matrices with 0 is less than or equal to h, which is less than 2, into 3 categories: positive semi-definite, virtual positive semi-definite, and generalized positive semi-definite, all based on specific conditions and matrix structures.
Okay, that sounds like a major milestone, a theorem that kind of brings all of these pieces together. So tell me about Theorem 3.9.
All right, so Theorem 3.9, it really is like the culmination of all the definitions, lemmas, propositions we've been discussing. It provides a clear framework for classifying h-Shuhan matrices when H falls between 0 and 2 based on their positive definiteness. And the theorem has 3 parts, each one dedicated to one of those positive definiteness categories.
Okay.
So let's start with the first part, which focuses on positive semi-definite matrices.
Okay, lead the way. I want to see how those trigonometric sequences and the matrix types that we talked about earlier, how they factor into this classification.
Okay, so the first part states that an h-Shuhan matrix with 0 is less than or equal to H, which is less than 2, is positive semi-definite if and only if it belongs to one of 5 very specific categories.
5 categories.
5 categories.
Okay, what are those categories and how do they connect to what we've learned so far?
Okay, so each category represents a specific matrix type and a condition on the value of H. And you'll recognize the matrix types, IN, DHN, A6, A7, and A8.
Okay, we've encountered all of those.
Right.
All right, what about the conditions on H? What role do those play?
So those conditions ensure that those corresponding trigonometric sequences that we talked about earlier, the ones associated with each matrix type, that those sequences are non-negative.
Okay.
So for instance, for an h-Shuhan matrix of type AN, the theorem says that it's positive semi-definite if and only if H is greater than or equal to 2 times cosine of pi over n plus 1.
Right.
Does that look familiar?
Yes, it does.
Yeah.
That's the same condition that we got earlier for the on sequence to be greater than or equal to 0.
You got it. It all comes back to those sequences. It's all beautifully interconnected. And the theorem provides similar conditions for each of those other matrix types, ensuring that those corresponding sequences are non-negative.
Okay. So this first part of Theorem 3.9, it's like a checklist.
Yeah.
If our h-Shuhan matrix matches one of those 5 types and H meets that corresponding condition, then we know for sure it's positive semi-definite.
Exactly. Powerful tool.
Okay, so that's positive semi-definite.
Yep.
What about the other 2 parts of the theorem? How do they handle virtual positive semi-definite and generalized positive semi-definite matrices?
Okay, so the second part focuses on virtual positive semi-definite matrices. It says that an h-Shuhan matrix with 0 is less than or equal to H, which is less than 2, is virtual positive semi-definite if and only if it's either already positive semi-definite, which we covered in the first part, or it belongs to one of 3 additional categories.
3 more categories.
Yeah.
Okay. How do these new categories differ from the positive semi-definite categories?
So these new categories also involve familiar matrix types,
Yeah.
BHAN, FH4, and GH2, each with a specific condition on H. But the main difference is that the conditions for these categories, they're a little bit less strict than the conditions for the positive semi-definite matrices. So they allow for the possibility that some of those submatrix determinants could be 0.
Okay, so we're spanning the criteria a little bit. We're still ruling out matrices with negative submatrix determinants, but now we're allowing for some zeros. It's like, being a little less picky about who gets into the club.
Precisely. Yeah. Good analogy. And then the third part of the theorem deals with generalized positive semi-definite matrices. It says that an h-Shuhan matrix with 0 is less than or equal to H, which is less than 2, is generalized positive semi-definite if and only if it's either positive semi-definite, back to the first part again, or it's of type BHN with a specific condition on H.
Okay, so for generalized positive semi-definite, the spotlight's on the BHN type. What's so special about BHN, and what's that condition on H?
So BHN, it's particularly interesting because its positive definiteness is closely tied to that largest eigenvalue MoN of the modified matrix B hat 0n that we discussed earlier.
Right, yeah.
And the condition on H here requires H to be greater than or equal to MoN.
Okay, so it all comes full circle. We're connecting the generalized positive semi-definiteness of BHN to the BHN sequence, to this largest eigenvalue MoN, even to that special constant epsilon. It's like we're weaving together all of these different strands to create this really detailed, beautiful mathematical tapestry.
Absolutely.
Okay, so Theorem 3.9, it really does bring everything together.
It does.
They have a really comprehensive framework now for classifying h-Shuhan matrices when H is between 0 and 2. based on their positive definiteness.
It really ties everything together.
This has been incredible. We've gone from basic definitions to these really intricate lemmas, propositions, even this central theorem. It's amazing how this paper just kind of methodically built upon itself to create this coherent and really fascinating exploration of these mathematical concepts.
It's a testament to the power of mathematical reasoning. And, you know, to wrap things up, there's one final proposition, proposition 3.15, that beautifully summarizes the classification of generalized Cartan matrices based on their generalized positive semi-definiteness and generalized positive definiteness.
Okay, a grand finale. What does this proposition reveal?
Okay, so proposition 3.15 states that a generalized Cartan matrix is generalized positive semi-definite if and only if it belongs to one of the following types, and I'm just going to list them off. A 2n, D2n, E26, E27, E28, B2n, where n is between 2 and 9, F24, G22, A121, A12n, D12n, E126, E127, and E128.
Okay, that's quite a list.
It is, yeah, and you'll notice a lot of those types have been popping up throughout this paper.
Yeah.
And so this proposition really brings them all together.
Okay, so what about generalized positive definite matrices? Does this proposition cover those as well?
It does. It says that a generalized Cartan matrix is generalized positive definite if and only if it's one of the following types. A 2n, D2n, E26, E27, E28, and B2n, where n is between 2 and 8. So notice B29 is excluded from that list.
Okay, so generalized positive definite, it's a little bit more exclusive.
Yeah. It makes sense the list is a bit shorter.
Right. Okay, so proposition 3.15, it really does tie a nice little bow on everything.
It does.
We've explored these really abstract definitions, and we've gone into these specific matrix types and uncovered the conditions that determine their positive definiteness, and now we have this clear classification of generalized Cartan matrices based on these properties.
Yeah, beautiful.
This deep dive has been fantastic. I really appreciate it. It's really given me a deeper appreciation for the interconnectedness and the beauty of these mathematical concepts.
Yeah, it is. It's remarkable.
What stands out to you as kind of the most remarkable takeaway from all of this?
I think for me, it's that intricate dance between h-Shuhan matrices and generalized Cartan matrices. It's really amazing how these seemingly distinct mathematical objects are so closely intertwined, and they reveal so much about the structure and classification of Lie algebras.
Yeah, it makes you wonder what other hidden patterns and connections are just waiting to be discovered out there.
Absolutely. It's a good reminder that even in a field as seemingly well-defined as mathematics, there's always more to explore and understand.
Well said. Well, thank you so much for guiding me through this deep dive. It's been a real pleasure.
Thanks for having me.
And until next time, keep those minds curious. Okay, where do we go from here? What other insights does this paper have for us about these h-Shuhan matrices?
Well, let's take a look at proposition 3.9 now. This one focuses on something called indecomposable affine generalized Cartan matrices.
Okay, now we talked about finite and affine types before.
Right.
But can you just remind me, what does indecomposable mean in this context?
Sure. So essentially, indecomposable means that the matrix can't be kind of split or broken down into smaller independent blocks. It's like a single solid unit.
Okay, so it's all of one piece. We can't break it apart without messing things up.
Exactly.
Okay, so what does this proposition tell us about these indecomposable affine types?
So this proposition, it reveals a very specific condition for when the associated h-Shuhan matrix, denoted as SURE, becomes virtual positive semi-definite.
Okay.
And it states that SURE is virtual positive semi-definite if and only if h is greater than or equal to 2.
Okay, so there's a clear threshold there for h. As soon as it hits 2 or goes above it, we know that corresponding h-Shuhan matrix for that indecomposable affine generalized Cartan matrix is going to be virtual positive semi-definite.
Exactly. It's a very straightforward but powerful condition for classifying these matrices. And it's interesting to me how a lot of the propositions and the theorems that we've discussed, they all kind of revolve around identifying these specific conditions on H that determine the positive definiteness of different types of matrices.
It seems like, yeah, the value of H is really, really the key to understanding these h-Shuhan matrices. It's like H is this control knob, and by adjusting it, we can change the fundamental properties of these mathematical objects.
Yeah. I like that way of thinking about it. It's a really good analogy.
Okay.
So moving on, proposition 3.11.
Okay. This
one delves into the generalized positive semi-definiteness of a few specific matrix types. These are G1H2, D3H4, F1H4, E2H6, and A2H2.
Okay, so we're getting into some really specific matrix types here.
Yeah.
Can you tell me a little bit about these matrices? What makes them stand out?
Sure. So each of these represents a particular structure of h-Shuhan matrices that often arises in certain applications. For instance, G1H2 is a 2x2 h-Shuhan matrix that is associated with a specific type of generalized Cartan matrix known as G2.
Okay.
And the others, D3H4, F1H4, E2H6, A2H2, they all represent h-Shuhan matrices that are linked to generalized Cartan matrices of types D4, F4, E6, and A2, respectively.
Okay. So again, we're connecting these h-Shuhan matrices back to those fundamental generalized Cartan matrices.
Yeah.
Okay. So what does proposition 3.11 tell us about the generalized positive semi-definiteness of these specific types?
Well, it basically gives us a specific condition on H for each of these matrix types to be generalized positive semi-definite.
Okay.
So, for example, it states that G1H2 and interestingly D3H4 as well are generalized positive semi-definite if and only if H is greater than or equal to the square root of 5.
So there's that threshold value for H again.
Exactly.
If it meets or exceeds that value, the square root of 5 in this case, then we know it fits that classification.
Precisely. And the proposition provides similar conditions for the other matrix types. So for F1H4 and for E2H6, H has to be greater than or equal to the square root of 17 over 2. And for A2H2, H needs to be greater than or equal to 5 over 2.
Okay. It's fascinating how each of these matrix types has its own kind of unique threshold value for H that determines its generalized positive semi-definiteness. Like they each have their own signature based on this value.
It's a good way to put it. It really highlights how, subtle variations in these matrices can lead to significant changes in their properties.
Right.
And these propositions, they give us a really nice set of tools for us to analyze and understand those subtle differences.
This has been a really insightful deep dive. We've gone from, basic definitions to these really complex lemmas and propositions, a central theorem. It's amazing how this paper so methodically builds upon itself to create this really coherent and fascinating exploration of these concepts.
I agree. It's really well written.
Yeah. And to wrap things up, I see there was one final proposition here, proposition 3.15.
Yeah.
What does this one have in store for us?
So proposition 3.15, it beautifully summarizes the classification of generalized Cartan matrices based on their generalized positive semi-definiteness and generalized positive definiteness.
Okay. A grand finale. Or what does it tell us?
So it states that a generalized Cartan matrix is generalized positive semi-definite if and only if it belongs to one of the following types. And I'm just going to rattle these off. A2n, D2n, E26, E27, E28, B2n for n between 2 and 9, F24, G22, A121, A12n, D12n, E126, E127, and E128.
Wow. Okay, that's quite the list. And I recognize a lot of those types from the propositions that we've already discussed.
Exactly. Yeah, they've been popping up throughout the paper, and this proposition just kind of brings them all together into one comprehensive classification.
Okay. What about generalized positive definite matrices? Does it classify those as well?
It does. It says that a generalized Cartan matrix is generalized positive definite if and only if it's one of the following types: a 2n, D2n, E26, E27, E28, and B2n for n between 2 and 8. So notice B29 is excluded from this list.
Oh, okay. So it's a little bit more exclusive there.
Exactly. Yeah, precisely. And so with that, proposition 3.15 really elegantly ties everything together. We've explored these abstract definitions. We've delved into specific matrix types. We've uncovered these conditions that govern their positive definiteness. And we've arrived at this very clear classification of generalized Cartan matrices based on these properties.
This has been fantastic. This deep dive has been a real journey. I've really come away with a deeper appreciation for just how interconnected and beautiful these mathematical concepts really are.
It is amazing.
What for you stands out as the most remarkable takeaway from all of this?
You know, I think it's got to be the intricate dance between h-Shuhan matrices and generalized Cartan matrices. It's just incredible how these seemingly distinct mathematical objects, they're so closely intertwined, and they reveal so much about the structure and the classification of Lie algebras.
It really makes you wonder what other hidden patterns and connections are out there just waiting to be discovered.
Absolutely. It's a great reminder that even in a field that seems, as well-defined as mathematics, there's always something more to explore and understand.
Well said. Well, thank you so much for guiding me through this deep dive. It's been an absolute pleasure.
Thanks for having me.
And until next time, keep those minds curious. Welcome to the deep dive. Today we're going deep into the world of matrices.
All right.
We got this paper, Positive Determinacy of h-Shuhan matrices with H2. And I got to say, just glancing at it, some of this stuff looks pretty intense. But luckily, we've got expert speaker here to help us break it all down.
Yeah, it's a really interesting paper for sure. It's all about figuring out when these special matrices have certain properties like, positive definiteness and those kind of things.
Right.
And that all ties into generalized Cartan matrices and even Lie algebras.
Right. Yeah, I see some terms in here that could probably use some explaining, like positive semi-definite, virtually positive semi-definite, even generalized positive semi-definite right there in the intro. So maybe before we jump into the paper, could you give us a little refresher on what all those mean?
Absolutely. So let's start with the most familiar one, which is positive semi-definite. A matrix is positive semi-definite if, for any vector x, you take x transpose times the matrix times x, and the result is always greater than or equal to 0. Essentially, it means the matrix never kind of flips the direction of a vector when it acts on it.
Right.
It can scale it, it can rotate it, but it won't send it in the opposite direction.
Okay, so it's like a force that's always pushing or pulling, consistently.
Exactly. Now, virtual positive semi-definite gets a little bit more specific. It means that not only is the whole matrix positive semi-definite, but so are all the smaller matrices you can make by deleting rows and columns.
Oh,
so you can take little sub-pieces of it.
So it's like that property has to hold at every level of the matrix.
Precisely. And then we have generalized positive semi-definite. This one's a bit trickier to visualize, but essentially it considers the average of the matrix and its transpose. So if that average matrix is positive semi-definite, then the original matrix is considered generalized positive semi-definite.
Okay, I think I'm following so far. So we had these three kind of levels of positive semi-definiteness, each with slightly different criteria.
Right.
And this paper is all about figuring out when these h-Shuhan matrices fit into these categories. But to be honest, I'm not even sure what an h-Shuhan matrix is yet.
Good point. The paper actually kind of introduces h-Shuhan matrices by connecting them to generalized Cartan matrices.
Okay.
It says that you can get a generalized Cartan matrix by taking an h-Shuhan matrix and adding 2h times the identity matrix. So to understand h-Shuhan matrices, we need to work backwards a bit.
Okay, so rewind back to generalized Cartan matrices. What are those and why are they important here?
So generalized Cartan matrices are really interesting objects that show up in various areas of math, especially in the study of Lie algebras. They have this very specific structure.
Okay.
All the entries on the diagonal are 2, all the off-diagonal entries are non-positive integers, and they have this symmetry where if you swap rows and columns, the matrix stays the same.
So it's a very structured type of matrix with some special properties.
Exactly. And the cool thing is, by subtracting 2Han times the identity matrix from a generalized Cartan matrix, we get an h-Shuhan matrix.
Yeah. So if I'm understanding this right, an h-Shuhan matrix is kind of like a generalized Cartan matrix, but with the diagonal entries replaced with h instead of 2.
That's a great way to put it. And the value of h plays a crucial role in determining the properties of the matrix.
Right.
The paper focuses specifically on the case where h is less than 2, which leads to some really interesting results.
Okay, so we've laid some groundwork here with positive semi-definiteness and these different types of matrices. What's the first big result the paper tackles?
So the paper starts by exploring the relationship between generalized positive semi-definite matrices and virtual positive semi-definite matrices.
Right.
And this is in lemma 1.2. It states that a matrix H is generalized positive semi-definite if and only if the matrix H, which is just the average of H and its transpose, is positive semi-definite in the traditional sense.
So this lemma is basically saying that these two seemingly different types of positive semi-definiteness are actually closely connected.
Right. And the proof is pretty straightforward. It just involves using the definition of generalized positive semi-definite matrices and showing that it's equivalent to requiring the averaged matrix to be positive semi-definite.
Gotcha. What about lemma 1.3? I see that one mentioned in the outline as well.
So lemma 1.3 is interesting because it talks about what happens when you add an antisymmetric matrix to a positive definite or positive semi-definite matrix. Remember, an antisymmetric matrix is one where if you swap rows and columns and change the sign, you get the original matrix back.
Right.
So the lemma states that if you add an antisymmetric matrix to a positive definite matrix, the determinant of the result is always greater than or equal to the determinant of the original matrix. And for positive semi-definite matrices, it says the determinant of the result is always greater than or equal to the determinant of the original matrix.
So it's like adding that antisymmetric matrix doesn't weaken the positive definiteness or semi-definiteness in terms of the determinant.
Exactly. And the proofs for both parts of the lemma rely on properties of determinants. And the fact that the determinant of an antisymmetric matrix is always 0.
Okay, and then proposition 1.4 brings those two lemmas together, right?
Exactly. Proposition 1.4 shows us that if a matrix is generalized positive semi-definite, it must also be virtually positive semi-definite.
Okay.
But the reverse isn't necessarily true. So generalized positive semi-definite is kind of a stricter condition.
Okay, that makes sense. So we've established this kind of hierarchy of positive semi-definiteness, with generalized being the most restrictive,
Right.
followed by virtual, and then the standard definition.
Yeah.
Now, where do these h-Shuhan matrices fit into all of this?
That's where things start to get really interesting. We need to jump to section 2, which really focuses on the properties of these h-Shuhan matrices and their connection to generalized Cartan matrices.
Okay.
And the paper delves into several lemmas and propositions that really help us understand their behavior.
All right, let's dive into those then. What's the first one we should tackle?
So the first one is lemma 2.1, and it's all about calculating the determinant of a matrix you get by adding a scaled identity matrix to another matrix. It's got two parts. The first part gives you a general formula for this calculation, and it involves determinants of principal submatrices.
Okay, wait, hold on. Remind me what a principal submatrix is again.
Sure. A principal submatrix is just a smaller matrix you get by choosing some rows of the original matrix and then keeping only the columns that correspond to those rows.
Okay.
So it's like you're taking a square chunk out of the original matrix.
Gotcha. That makes sense. So lemma 2.1 gives us a way to calculate the determinant of a matrix that's been, modified by adding a multiple of the identity matrix.
Exactly. The formula itself can look a little bit complicated, but the key idea is that it breaks the determinant down into terms involving determinants of these smaller submatrices
Okay.
and powers of the scaling factor.
And what about the second part of the lemma?
The second part gives a more specific formula for the case where you're adding a scaled identity matrix, denoted as LEE, to a matrix H. It's essentially a specialized version of the first part. Again, it expresses the determinant of this modified matrix in terms of determinants of submatrices of H.
Okay.
And powers of all.
Okay, so lemma 2.1 gives us these tools for calculating determinants. Where does the paper go from there?
From there, it moves on to proposition 2.2, which establishes a very important property of virtually positive semi-definite matrices. It states that if a matrix is virtually a positive semi-definite, all its eigenvalues must be non-negative.
That's a pretty big deal. Eigenvalues tell us a lot about how a matrix behaves. So knowing they have to be non-negative for virtually positive semi-definite matrices gives us some powerful insights. How does the paper prove that?
So the proof is actually quite clever. It uses the fact that determinants of principal submatrices have to be non-negative for a virtually positive semi-definite matrix.
Right.
By cleverly choosing specific submatrices and analyzing their determinants, they're able to show that any negative eigenvalue would lead to a contradiction.
So it's kind of like a proof by contradiction.
Yeah.
Where they show that assuming a negative eigenvalue leads to an impossible situation.
Exactly. And this result actually leads to some interesting connections with the classification of generalized Cartan matrices. And this is where lemma 2.3 comes in.
Okay, let's hear about lemma 2.3 then.
So lemma 2.3 focuses on a specific type of generalized Cartan matrix called an affine generalized Cartan matrix. These matrices have the interesting property that their determinant is 0, but all their principal minors are non-negative. So they're kind of right on the edge of being invertible,
Right.
but they still maintain this positive semi-definite character in all their submatrices.
Interesting. So these affine matrices are like a special case that walk a fine line between, invertibility and non-invertibility.
Exactly. And this lemma is crucial for understanding proposition 2.4, which really connects virtual positive semi-definiteness to the classification of generalized Cartan matrices.
All right, proposition 2.4 sounds like it's getting to the heart of things. Tell me more.
So proposition 2.4 is a multi-part statement that really ties a lot of these concepts together. First, it says that a generalized Cartan matrix is virtually positive semi-definite if and only if it's either a finite or affine type.
Right.
So this establishes virtual positive semi-definiteness as a kind of characteristic property of these two types of generalized Cartan matrices.
So that's like saying if you know a matrix is virtually positive semi-definite, you immediately know something about its broader classification.
Exactly. The second part of the proposition is about how adding a positive multiple of the identity matrix can boost a virtually positive semi-definite matrix to being virtually positive definite.
Okay.
And it applies this specifically to h-Shuhan matrices, saying that if h is less than 2 and the h-Shuhan matrix is virtually positive semi-definite, you can make it virtually positive definite by adding a suitable multiple of the identity matrix.
So it's like you can push it over the edge from semi-definite to definite by adding in a bit of the identity matrix.
Precisely. And then the third part is kind of the reverse. It says that if h is greater than 2, and you get a finite or affine type generalized Cartan matrix by adding a multiple of the identity matrix to an h-Shuhan matrix,
Okay.
then the original h-Shuhan matrix must already have been virtually positive definite.
So it's like a two-way street between these h-Shuhan matrices and generalized Cartan matrices.
Right.
And the value of h plays a big role in determining which properties hold.
Exactly. And that's a great point to kind of transition into section 3.
Okay.
Because that's where the paper really starts to dig deep into the specifics of h-Shuhan matrices when h is less than 2.
Okay, I'm ready for section 3. What's the first thing they tackle there?
So they start off by introducing a bunch of new notations and recursive formulas that are going to be important for their analysis.
Recursive formulas. Those always make my head spin a little.
I know what you mean, but they're actually pretty cool once you get the hang of them.
Okay.
Basically, instead of having a direct formula for something, you define it in terms of previous values in a sequence.
Gotcha. Can you give me an example of one of these recursive formulas?
Sure. One of the first ones they introduce is for a variable called on. They define on as h times on1 minus on2.
Okay.
So to calculate on, you need to know the values of on1 and on2.
So it's like a chain where each link depends on the ones before it.
Exactly. And they do this for several variables: on, bn, dn, naj. These variables are all related to determinants of specific matrices they're going to analyze later.
Okay, so it's like they're setting up these building blocks that'll help them understand the bigger picture.
Exactly. And once they've laid out these recursive definitions, they start proving some lemmas that give us more insight into these variables.
Like what kind of insights?
Well, for example, lemma 3.1 gives us an explicit formula for on when h is not equal to 2.
Okay.
It's a bit of a mouthful, but it basically expresses on in terms of h and on using exponents and square roots.
So instead of needing to calculate it recursively, we have a direct formula we can use.
Exactly. And then lemma 3.2 focuses on the case where h is between 0 and 2, which is the range the paper is primarily interested in. This lemma gets really interesting because it brings in trigonometry.
Trigonometry. What does that have to do with matrices?
It's actually pretty cool. Lemma 3.2 expresses on, b8n, and dhn in terms of sine and cosine functions using an angle that's related to h.
So it's like they're using the cyclical nature of trigonometric functions to understand the behavior of these matrix determinants.
Exactly. And this representation is particularly useful for analyzing when these variables are positive or negative. The lemma establishes conditions on h in terms of cosine functions that guarantee the non-negativity of on hn and dhn.
Okay, I can see how that would be helpful.
Right.
Especially since we're interested in positive definiteness.
Right.
So these lemmas are all about laying the groundwork for understanding these, key variables. Where do we go from there?
From there, we move to proposition 3.3. which starts to apply these lemmas to specific types of matrices. It's a long proposition with several statements, but the overall theme is establishing conditions for when these matrices are positive semi-definite or virtually positive semi-definite.
Okay, can you give me an example of one of those conditions? Like for a specific type of matrix, what does the proposition tell us?
Sure. Let's look at matrices of the form BAN. Proposition 3.3 says that BHN is virtually positive, semi-definite, if and only if H is greater than or equal to 2 times the cosine of divided by 2.
So the value of H has to exceed a certain threshold that depends on the size of the matrix.
Right.
In order for it to be virtually positive, semi-definite.
Exactly. And the proofs for these statements in Proposition 3.3 involve showing that all the relevant determinants are non-negative under the given conditions.
So there's a lot of careful analysis of determinants using the tools and formulas they've developed in the previous lemmas.
Exactly. And that's actually where we'll pick things up in Part 2 of our deep dive.
Sounds good.
Yeah.
This is already pretty mind-bending stuff, so I think a break is definitely in order. Listeners, be sure to come back for Part 2, where we'll continue exploring this fascinating world of h-Shuhan matrices.
Yeah, it'll be fun. Welcome back to the deep dive. We're picking up with Section 3, where we're looking at these h-Shuhan matrices.
Right, yeah. Things were getting pretty intense before the break with all those recursive formulas and trigonometry. I'm still trying to wrap my head around how that all fits together.
Yeah, it's definitely a lot to take in. But it all comes down to understanding the conditions for positive definiteness of these matrices.
Right, and we were talking a lot about determinants and how they play a big role in all of that.
Exactly.
But before we dive back into the specifics, can you remind me again, like, why are determinants so important when we're talking about positive definiteness?
That's a great question. So determinants basically tell us about the volume scaling effect of a matrix.
Okay.
If you think of a matrix as a transformation that kind of stretches and squashes space, the determinant tells you how much the volume of a unit cube changes after that transformation.
Okay.
So if the determinant is positive, the volume increases or stays the same, meaning the transformation doesn't collapse any dimensions.
Right.
That's why positive determinants are closely tied to positive definiteness.
Ah, okay, that makes a lot of sense. So for positive semi-definite matrices, we want to make sure they don't completely flatten any directions, right?
Right.
And that's reflected in this requirement for non-negative determinants.
Exactly. Now, the paper introduces a new concept called n, and this is defined as the largest real number that makes the determinant of a specific matrix denoted as Bn equal to 0.
Okay, so n is like the tipping point where the matrix loses invertibility.
Right.
But why is that important? Like, why are we focusing on that?
Because it helps us establish even tighter bounds on the values of h that guarantee positive definiteness.
Okay.
The authors claim that n increases as n gets larger, but always stays below a certain constant value, which they call a, and approximate as 2.04998. And they actually devote several lemmas to proving this.
So there's this kind of invertibility zone for A
Yeah.
that gets narrower as the matrix grows, but it always stays above this critical value there.
Precisely.
So what are those lemmas that prove all that?
So the first one is lemma 3.4, which proves that A is strictly increasing.
Okay.
So as the matrix gets bigger, the upper bound on H for invertibility also gets bigger, but it never decreases.
So n is always climbing higher as n increases.
Right. Then lemma 3.5 establishes that n is always trapped between 32 and 8.
Okay.
It can never go below 32, and it can never actually reach A, only approach it as n goes to infinity.
So it's like n is a climber on an infinite ladder, always going up, but never quite reaching the top.
I like that analogy. That's a great way to put it. And to prove these lemmas, they use a combination of induction and some clever manipulations of the recursive formulas that we talked about earlier.
Right, so it sounds like a lot of intricate mathematical acrobatics.
It is, but it's also really elegant, you know? And those two lemmas lead to a very important corollary 3.6.
Okay.
Which states that if H is greater than or equal to A,
Right.
the matrix BHN is generalized positive definite for any n greater than or equal to 2.
So exceeding that error value gives Bn a lot of stability and ensures it always exhibits this generalized positive definite behavior no matter how large it gets.
Precisely. And that sets the stage for proposition 3.7, which really dives into the specifics of when BH is generalized positive semi-definite for values of h between 0 and 2.
All right, tell me about proposition 3.7. What's it say?
Okay, so the proposition establishes that for 0h2, BHn is generalized positive semi-definite if and only if h is greater than or equal to n for values of n from 2 to 8. It even provides explicit formulas for these n values, some of which involve trigonometric functions and their inverses.
Wow, those formulas look pretty intense. Why do they need to bring in trigonometry there?
Yeah, the authors actually address that in remark 3.8. They explain that for some of these onion values, like 8, you can't express them using only roots of real numbers. So they need to use these more advanced trigonometric expressions to capture their exact values.
Wow, so even something as seemingly simple as figuring out when a matrix is positive semi-definite can lead to some really deep and complex math.
Yeah, it really does. And it highlights the power of different mathematical tools and how they can all work together to shed light on these problems.
Absolutely. Now, where does the paper go from there? Does it move on to other types of matrices?
It does. The paper builds up to theorem 3.9, which is kind of like the grand finale of this section.
Okay.
It provides a complete classification of h-Shuhan matrices when h is less than 2, based on whether they're positive semi-definite, virtually positive semi-definite, or generalized positive semi-definite.
Okay, so theorem 3.9 is like a culmination of all the previous work.
Right.
It tells us exactly when each of these properties holds for different types of h-Shuhan matrices.
Exactly, and it does this by dividing h-Shuhan matrices into several categories based on their structure and the value of h.
Okay.
And for each category, it gives specific conditions on h that determine which type of positive semi-definiteness holds.
Can you give me an example, like one of those categories and its condition?
Sure. Let's look at matrices of the form AN.
Okay.
The theorem states that AN is positive semi-definite if and only if h is greater than or equal to 2 times the cosine of divided by n plus 1.
So the condition depends on both h and the size of the matrix n.
Exactly. And the theorem goes on to list conditions for several other categories of matrices, including BHN, ANN, FH4, and G2. It's a really comprehensive classification.
It sounds like a powerful tool for anyone working with these h-Shuhan matrices.
It is.
It gives them a clear roadmap for understanding when these key properties hold.
It does. It's a testament to the, careful and systematic approach that the authors have taken throughout the paper.
Right.
They've laid out this series of lemmas and propositions that build on each other, culminating in this really elegant and powerful theorem.
I'm really impressed by the level of detail and rigor in this paper. It's clear that a lot of thought and effort went into it.
Absolutely. Now, the paper doesn't stop there.
Oh.
It goes on to explore some additional propositions that extend these results to other specific types of matrices, like indecomposable affine generalized Cartan matrices, and matrices of the form B1HN and C1HN.
Okay, so tell me about those additional propositions. What do they reveal?
So, for example, proposition 3.10 focuses on these indecomposable affine generalized Cartan matrices.
Okay.
Remember, these are the ones with determinant 0 but non-negative principal minors.
Right.
The proposition states that if you transform such a matrix into an h-Shuhan matrix using the usual method, it will be virtually positive semi-definite if and only if h is greater than or equal to 2.
So it's giving us a very specific condition for virtual positive semi-definiteness in this particular case.
Exactly. And then proposition 3.11 looks at 3 specific types of generalized Cartan matrices and establishes conditions for their generalized positive semi-definiteness.
Okay.
For instance, it says that a matrix of the form G1H2 is generalized positive semi-definite if and only if h is greater than or equal to the square root of 5.
So each of these propositions is like a specialized lens that helps us understand the properties of these matrices in even more detail.
That's a great way to put it. And they all rely on the foundations laid out in the earlier lemmas and theorem 3.9.
Right now, I noticed that the outline also mentions lemma 3.12.
Yes.
Which sounds like a pretty technical one.
It is.
What's its role in all this?
So lemma 3.12 is interesting because it introduces a chain of inequalities for determinants of specific matrices under certain conditions. It's a bit technical to explain in detail, but essentially it establishes that if a certain pattern holds for smaller matrices, it must also hold for larger ones.
So it's like a domino effect.
Yeah.
Where a property proven for smaller matrices cascades up to larger ones.
Exactly. And this lemma is actually crucial for proving proposition 3.13,
Right.
which deals with the generalized positive semi-definiteness of matrices of the form B1HN and C1HN.
Okay, so tell me about proposition 3.13. What does it say about those matrices?
So it provides specific conditions for their generalized positive semi-definiteness based on the value of h.
Okay.
For B1HN, it states that it's generalized positive semi-definite if and only if h is greater than or equal to the square root of 17 divided by 2.
Okay.
And for C1HN, it's generalized positive semi-definite if and only if h is greater than or equal to 3 times the square root of 2 divided by 2.
So just like with the previous propositions, it's all about pinpointing those critical thresholds for h
Right.
that guarantee the desired property.
Precisely. And to prove these statements, they cleverly utilize lemma 3.12, showing how those chains of inequalities for determinants actually play a key role in establishing these conditions.
Man, it's amazing how all these pieces fit together, you know?
That is.
Each lemma and proposition kind of builds on the previous ones and creates this really intricate and beautiful mathematical structure.
I agree. And just when you think they've covered every possible case, they throw in remark 3.14, which is a brief but important observation.
Oh.
It points out that all the results they've discussed so far, which focus on positive semi-definiteness,
Right.
also apply to positive definiteness if you just replace all the greater than or equal to signs with greater than signs.
So it's like they've done double the work with half the effort. They've established this whole parallel set of results for positive definiteness just by tweaking the inequality.
Exactly. It's a really elegant way to extend their findings without having to redo all the proofs.
And finally, we reach the last proposition in the paper, proposition 3.15.
Yes.
What's the grand finale all about?
So proposition 3.15 provides a comprehensive classification of generalized Cartan matrices based on whether they're generalized positive semi-definite or generalized positive definite. It essentially lists out all the generalized Cartan matrices that fall into each category.
So it's like a culmination of everything we've been discussing.
Right.
It tells us which generalized Cartan matrices possess these important properties based on their structure.
Precisely. It's a powerful result that summarizes a lot of the key findings of the paper.
Wow, we've really covered a lot of ground. It's been quite a journey through the world of these h-Shuhan matrices and generalized Cartan matrices and positive definiteness.
It has. But I think we've only scratched the surface. There's so much more to explore in this fascinating area of mathematics.
I agree. This deep dive has definitely piqued my curiosity.
Yeah.
Before we wrap things up, is there anything else from the paper you'd like to highlight or any final thoughts you'd like to share?
I think one of the most important takeaways from all this is the interconnectedness of these concepts, you know?
Right.
We've seen how these kind of abstract definitions and technical lemmas can lead to these powerful theorems and a deeper understanding of the structure and properties of these matrices.
Right.
It's a beautiful example of how different areas of math can all come together to shed light on these complex problems.
Yeah, and it highlights the importance of both rigor and creativity in mathematical research.
Absolutely.
So all this work has been very theoretical.
Yeah.
Do you have any thoughts on how these results could be applied in practice? I mean, we've mentioned Lie algebras a few times, but are there any concrete ways that these findings could be useful?
That's a great question. And, you know, it's one that mathematicians often grapple with, the bridge between theory and application. In this case, I think the potential applications are vast, but they might not be immediately obvious. So remember, Lie algebras are used to study symmetries.
Right.
And symmetries are everywhere in mathematics and physics.
So that connection to symmetries is key.
Exactly. For example, in physics, Lie algebras are used to describe the symmetries of physical systems, the symmetries of particles or the symmetries of space-time. And understanding those symmetries is really crucial for developing theories that can accurately describe the universe.
Right.
So by deepening our understanding of generalized Cartan matrices, which are fundamental to the study of Lie algebras, we're indirectly contributing to those areas of physics as well.
That's really cool. So we're laying the groundwork for future discoveries in physics, even though we're working in this purely mathematical realm.
Precisely. And it's not just physics.
Wow.
Lie algebras also have applications in areas like engineering, computer science, even economics.
Wow.
Anywhere you have these complex systems with underlying symmetries, Lie algebras can be used to analyze and understand them.
So the potential impact of this research is really far-reaching.
It is, and that's what I find so exciting about mathematics.
Yeah.
Even the most abstract and seemingly esoteric concepts can have these profound implications for the world around us.
Absolutely. Well, this has been a truly enlightening conversation. Thank you so much for guiding us through this fascinating mathematical landscape.
It was my pleasure. I always enjoy exploring these fascinating mathematical ideas.
And to our listeners, we hope this deep dive has inspired you to learn more about h-Shuhan matrices, generalized Cartan matrices, and the amazing world of Lie algebras. Until next time, keep diving deeper into the world of knowledge. Welcome back, everyone, to the deep dive. This time, we're going to unpack some fascinating research on h-Shuhan matrices.
Ah, yes, these matrices, they really are more than meets the eye.
I've been skimming through this paper by Wu and Yang, Positive Determinacy of h-Shuhan matrices with h less than 2. It's dense, but intriguing. I'm ready to dive in with you.
Excellent. Let's start with the basics. What makes a matrix a Shuhan? Well, Wu and Yang lay out 3 conditions.
3 conditions.
Yep, S1, S2, and S3. S1 is all about the diagonal entries. They all have to be equal to a non-negative real number, which they call H.
So H is like the matrix's defining characteristic.
Exactly. Think of it as the matrix's signature. Now, S2 focuses on the off-diagonal entries. They got to be non-positive integers.
Okay, so we're dealing with a specific kind of structure right from the start.
Right. And then S3 adds another layer of complexity. It says that for any 2 off-diagonal entries that are mirrored across the main diagonal, either they're equal or one is strictly less than the other, and the larger one has to be -1.
Interesting. It seems like these conditions are setting the stage for some pretty specific matrix behavior.
Absolutely. And these conditions are crucial for connecting h-Shuhan matrices to those generalized Cartan matrices I mentioned earlier. Remember, those are the blueprints for classifying Lie algebras.
Right. Those powerful algebraic structures we've talked about before. So h-Shuhan matrices are a stepping stone to understanding even bigger math concepts.
Precisely. Now, before we get too lost in the weeds, let's make sure we're all speaking the same mathematical language. Wu and Yang use a lot of symbols.
Yeah, I noticed that. A little cheat sheet might be helpful.
Definitely. They use standard notation like, H for the matrix itself, R for the set of real numbers, Z for integers, N for natural numbers, Q representing rational numbers.
Okay, those are familiar. What about some of the less common symbols?
Well, they use Sn for the symmetric group on N elements.
Got it. What about the V with the subscript N?
Ah, right. That's Vn, representing the set of all n-dimensional column vectors with real number entries. And is simply the set of indices from 1 to n.
Okay, I'm following so far. Anything else we should keep in mind?
They use H to denote the determinant of the matrix H, and hi1, I2 to represent those algebraic cofactors after removing certain rows and columns, essentially creating a smaller submatrix.
Right, like focusing on a specific part of the matrix.
Exactly. And his1, I2 represents the specific submatrix at the intersection of those rows and columns without changing their original order in the matrix.
Got it. So it's all about being precise with our mathematical language.
Precisely. Now let's get to the heart of the matter. Positive definiteness and semi-definiteness, and their variations.
Yeah, let's unpack those concepts. I remember we've touched upon them before, but a refresher would be helpful.
Of course. Imagine a positive definite matrix, like a rubber ball, an unyielding one.
Okay, I like where this is going.
No matter how you push it, it always springs back. Mathematically, this means that when you multiply a positive definite matrix by a non-zero vector and its transpose, the result is always a positive number.
So it's like the matrix is always pushing back.
Exactly. Now, a positive semi-definite matrix is like a slightly less springy ball. It might not always spring back with the same force, might even stay put in some directions.
So it's a bit more flexible.
You got it. Mathematically, this means the result of that multiplication can be 0 for some vectors, not always strictly positive.
Okay, that makes sense. Now, Wu and Yang also throw in virtual positive semi-definiteness and generalized positive semi-definiteness into the mix. What's the difference?
Good question. A virtually positive semi-definite matrix means all the determinants of its principal submatrices are non-negative. Picture taking smaller and smaller squares from the top left corner of the matrix and making sure all their determinants are non-negative.
Okay, so it's about those submatrices and their determinants. What about generalized?
Generalized positive semi-definite means that multiplying the matrix by any vector and its transpose always gives a non-negative number. It's like regular positive semi-definiteness, but with a broader scope.
Interesting. It seems like these different types of semi-definiteness are adding nuances to the way we analyze these matrices.
Absolutely. And the paper highlights that for symmetrical matrices, all three types of semi-definiteness are actually equivalent.
Oh, that's interesting. So it's like different paths leading to the same mathematical truth.
Exactly. Now, here's where things get really interesting. The paper explores how the value of H, remember that defining characteristic of h-Shuhan matrices, can actually determine whether the matrix is positive semi-definite or not.
Okay, so the value of H is crucial. What did they find?
Well, this is where it gets a bit unexpected. Trigonometry enters the picture.
Trigonometry, like sines and cosines. I didn't see that coming.
It's a beautiful example of how seemingly unrelated areas of math can be deeply connected. Wu and Yang show that for certain h-Shuhan matrices to be positive semi-definite, H has to be greater than or equal to 2 times the cosine of specific fractions of pi.
Wow, okay. Can you give us a concrete example?
Sure. Take a type of matrix called AN. For it to be positive semi-definite, H must be greater than or equal to 2 times the cosine of pi divided by n plus 1, where n is the size of the matrix. This relationship emerges from the structure of the matrix and those conditions for positive semi-definiteness we talked about earlier.
So the value of H sets a threshold for the matrix's behavior.
Exactly. And each type of h-Shuhan matrix has its own unique threshold involving those trigonometric functions. Like for a matrix called BHS, H has to be greater than or equal to 2 times the cosine of pi divided by 2n.
Wow, it's amazing how this single parameter H can have such a profound impact on the entire matrix.
It really is, and this connection to trigonometry hints at even deeper mathematical structures at play. Remember those Lie algebras and generalized Cartan matrices?
Oh, they're always lurking in the background, aren't they? It's what makes this whole exploration so fascinating.
Exactly. Now, the paper goes deeper, introducing lemmas and propositions to really unpack these relationships. For example, Lemma 3.1 gives us a formula for calculating the determinant of a specific type of h-Shuhan matrix.
Right, that formula for on. I remember it involved powers of H and some square roots.
Yep. It might look a bit complex at first glance, but it's a key step in understanding how H affects these determinants. It's like a building block for the bigger picture.
So Lemma 3.1 lays the foundation. What about Lemma 3.2?
Lemma 3.2 brings in that trigonometry we were talking about. It says that for 0 less than or equal to h less than 2, we can express on, BSENN, and DN, the determinants of certain matrices using sine and cosine functions of an angle.
Wait, so we're using trigonometry to represent determinants? How does that even work?
It's all about recognizing patterns and applying those trigonometric identities. Remember that formula for on from Lemma 3.1? Well, if you substitute h with 2 times the cosine of h, you get something that resembles the formula for sine of n plus 1 divided by sine of it.
So it's a clever substitution to reframe the determinant formula.
Precisely. And this trigonometric representation leads to some interesting insights. For example, Lemma 3.2 tells us that on is greater than or equal to 0 if and only if h is greater than or equal to 2 times the cosine of pi divided by n plus 1.
So we're using trigonometry to understand the conditions for positive semi-definiteness.
Exactly. It's like we're uncovering hidden connections between these different areas of math.
I'm starting to see how these lemmas are building towards something bigger. Where do they lead us?
They lay the groundwork for Proposition 3.3, which gives us specific conditions for various h-Shuhan matrices to be positive semi-definite, based on the value of h.
So it's like we're constructing a toolbox for analyzing these matrices, and each lemma is a new tool.
Exactly. And Proposition 3.3 provides those concrete examples you mentioned earlier. It states, for instance, that a matrix called A6 is positive semi-definite if and only if h is greater than or equal to 2 times the cosine of pi divided by 12.
So each type of matrix has its own trigonometric threshold for positive semi-definiteness.
Precisely. And then comes this interesting concept of n, which is the largest real number that makes the determinant of a certain type of matrix called n equal to 0.
Right, and it's like a tipping point, right? If h is less than n, the matrix isn't positive semi-definite. But if h is greater than or equal to n, it might be.
Exactly. It's like a boundary between definite possibilities and uncertainty.
So understanding n helps us narrow down the range of h values that we need to consider for positive semi-definiteness.
Precisely. And Wu and Yang uncover some pretty remarkable properties of this n. For instance, Lemma 3.4 proves that n always increases as the size of the matrix. n increases. They use proof by contradiction to show this.
Ah, proof by contradiction, a classic mathematical technique.
It's like setting a trap for a false assumption.
And if it falls into the trap, you know it must be wrong.
Exactly. In this case, they show that if 9 didn't increase with n, you'd end up with a mathematical absurdity, a contradiction. So a twine has to keep climbing higher as the matrix grows.
It's like n is on this never-ending upward journey as the matrix expands.
But there's a catch. It can't climb infinitely high. They introduce a value GAN, which is about 2.04998, and they prove in lemma 3.5 that no matter how large n gets, always stays less than e.
So n is always increasing, but it has a ceiling, it's bounded. What's the significance of this A's value? It seemed to pop up out of nowhere.
It turns out ed is far from random. It's the largest real root of a specific polynomial equation that's closely tied to the structure of these matrices. By analyzing this equation, Wu and Yang demonstrate that the determinant of Binon is always positive for any h that's greater than enc.
So they found a way to guarantee a certain behavior for this matrix just by looking at the value of...
Exactly. And because n is the value that makes the determinant 0, it has to stay below this n. It's always climbing, but it can never reach the top.
It's trapped between two boundaries, always increasing, but forever bound by ang.
A fascinating mathematical dance. Now, these bounds on n lead to a powerful conclusion, which is stated in corollary 3.6. It says that if h is greater than or equal to, then the matrix Ben is always generalized, positive definite, no matter how big the matrix gets.
So we can guarantee a certain property for this entire class of matrices just by choosing a large enough h. It's like we've gained a deep understanding of its behavior just by focusing on this one parameter.
Precisely. And this insight has far-reaching implications, especially when we connect it back to those Lie algebras we've been discussing.
Right, the plot thickens. Now, I appreciate that the paper doesn't just throw abstract concepts at us. They provide concrete calculations and examples to illustrate these ideas.
Absolutely. They calculate specific values of nn ranging from 2 to 8, some of which involve those trigonometric functions.
Right, I saw that. And they even explain, in remark 3.8, why certain values of dating can't be expressed using simple radicals.
Ah, yes, that delves into some fascinating territory, Galoha theory, which deals with the solvability of polynomial equations. Essentially, they're showing us that even though we can pin down taunt for some values of bin, for others, it's a bit more elusive, a bit more mysterious.
So we're not only exploring the properties of these matrices, but also touching upon deeper questions about the nature of numbers themselves.
Exactly, and that's what makes this research so compelling. It's a journey into the very foundations of mathematics.
I'm ready for the main event now. What's the key takeaway from all of this?
The culmination of all this groundwork is Theorem 3.9. It provides a complete classification of when an h-Shuhan matrix with each less than 2 is positive semi-definite, virtually positive semi-definite, or generalized positive semi-definite.
So it's like the grand finale, the pièce de résistance.
Exactly. It ties everything together, showing us all the possibilities depending on the structure of the matrix and the value of h.
Wow, that sounds like a powerful result. And then propositions 3.1 and 3.11 extend these results to specific types of matrices based on generalized Cartan matrices.
Right. They're building upon Theorem 3.9, taking it further and showing how it applies to these specific cases.
It's like we're constructing a whole framework for understanding these matrices and their connection to those broader concepts.
And then there's remark 3.14. They highlight a subtle but important point. All of these results about semi-definiteness still hold if we replace semi-definite with definite and change the inequalities to strict inequalities.
So it's like they're showing us that their conclusions are robust, they hold up under different mathematical lenses.
Precisely. And finally, proposition 3.15 brings everything full circle, connecting it back to those generalized Cartan matrices and their classification. It's like we've completed a loop showing how these seemingly specific h-Shuhan matrices provide valuable insights into these broader algebraic structures.
Wow, we've covered an incredible amount of ground already. We started with those 3 simple conditions, defining a h-Shuhan matrix, explored the crucial role of h and its unexpected connection to trigonometry, and arrived at a comprehensive classification based on their definiteness properties. This is just the beginning, right?
You got it. Now that we've laid the groundwork, we can really get into the nitty-gritty. In the next part, we'll explore the proofs behind these remarkable findings. We'll roll up our sleeves and see how Wu and Yang constructed this intricate mathematical edifice.
I'm ready to dive deeper into those proofs. This is where the real beauty lies.
Let's do it.
We've explored the landscape of h-Shuhan matrices and their fascinating properties, and now I'm ready to uncover the logic behind them. Let's dive into those proofs.
Right. Unpacking the proofs is where we really get to appreciate the elegance of Wu and Yang's approach. Remember that formula from Lemma 3.1, the one for the determinant of an h-Shuhan matrix?
You mean the formula for on? The one with the powers of h and those square roots? Yeah, it looked a bit intimidating at first.
It does seem complex, but it's actually quite structured. The formula says that for h not equal to 2, we can express the determinant of on using powers of h plus or minus the square root of h squared minus 4, all divided by the square root of h squared minus 4. But the real question is, how do we know this formula actually works?
Right. How do we prove it's not just some mathematical coincidence?
The proof relies on mathematical induction. Think of it like building a tower brick by brick.
Okay, I'm picturing it.
First, you prove the formula holds true for the simplest case, the base case. Usually that's when n equals 1 or 2. It's like laying the foundation of our tower.
Okay, we start with the simplest case. Then what?
Then we make an assumption. We assume the formula holds true for some arbitrary value of n, let's say k. It's like assuming we've already built the tower up to the kth floor.
So we're assuming the formula works up to a certain point?
Exactly. And using this assumption, we try to prove that the formula must also work for the next level, for n equal k plus 1. This is the crucial step. We're showing that if it works for one floor, it must work for the floor above it as well.
So if we can build one more floor, we're proving the entire tower is structurally sound.
Exactly. And since we already proved it works for the base case, our foundation, this logic continues infinitely upwards. We've essentially proven the formula works for all values of n. Our tower can reach the sky.
It's fascinating how mathematicians can prove these abstract concepts through such logical structures.
It's the power of reasoning. Now, Lemma 3.2 takes this determinant formula and brings in trigonometry.
Trigonometry.
Yep. It states that for 0 less than or equal to h less than 2, we can express those determinants on BHN and DHN using sine and cosine functions.
Hold on, how do sines and cosines even come into play here? We're dealing with determinants, not triangles.
It's all about pattern recognition. Remember that formula for on from Lemma 3.1? Well, if we substitute h with 2 times the cosine of an angle, let's call it Terry, we get an expression that looks a lot like the formula for sine of n plus 1 divided by sine of on.
So it's like a clever substitution using trigonometry to rewrite the determinant formula.
You got it. And this new form leads to some interesting observations. Lemma 3.2 also tells us that on is greater than or equal to 0 if and only if h is greater than or equal to 2 times the cosine of pi divided by n plus 1.
So we're linking trigonometry to the idea of positive semi-definiteness.
Precisely. We're using trigonometry to understand those conditions.
But how do we prove that this condition is both necessary and sufficient for on to be non-negative?
We need to dig deeper into trigonometric identities and inequalities. Since 0 is less than or equal to h less than 2, we can express h as 2 times the cosine of an angle 3, where 0 is less than or equal to pi divided by 2. Using the properties of sine and cosine, we can show that on is greater than or equal to 0 if and only if n plus 1 is less than or equal to pi.
Okay, I'm following. So that leads to the condition that h must be greater than or equal to 2 times the cosine of pi divided by n plus 1.
Exactly. We're using trigonometry as a tool to reveal the properties of these determinants.
It's like a mathematical lens focusing on those hidden properties.
I like that. Now, these lemmas we've been talking about, they pave the way for Proposition 3.3, which lays out specific conditions for various h-Shuhan matrices to be positive semi-definite based on the value of h.
Right, Proposition 3.3. It said that a matrix like A is positive semi-definite if and only if h meets that trigonometric condition we just discussed. It's like each matrix type has its own trigonometric password.
That's a good way to put it. And the proof of Proposition 3.3 relies on connecting the positive semi-definiteness of the matrix to the non-negativity of its principal minors. Remember, for a matrix to be positive semi-definite, all those subdeterminants need to be non-negative.
So we need to show that all those smaller determinants are following the rules.
Exactly. And we can use those formulas from lemmas 3.1 and 3.2 to do just that. We apply them to these specific matrix structures, showing that when h meets the trigonometric condition, all those principal minors fall in line.
It's impressive how those lemmas, which seemed abstract at first, provide the tools we need to tackle these bigger propositions.
They're the building blocks of our understanding. And Proposition 3.3 goes on to establish similar conditions for other matrices like BH and DHN, A6, and so on. Each one has its own unique trigonometric threshold for h, a point where it transitions to positive semi-definiteness.
We're mapping out the boundaries of these mathematical landscapes, aren't we?
A very precise map indeed. Now, do you remember that largest real number that makes the determinant of bm equal to 0?
Right. Yeah, that tipping point. If h is less than n, the matrix is definitely not positive semi-definite. But if h is greater than or equal to n, it's a maybe.
Exactly. It's like a boundary between what we know for sure and what's still uncertain.
So finding n helps us narrow down the possibilities for positive semi-definiteness.
Absolutely. And Wu and Yang uncover some really cool properties of the same. For example, lemma 3.4 shows that n always increases as the size of the matrix. N increases.
So as the matrix grows, n keeps climbing higher.
Exactly. And the proof uses a clever technique called proof by contradiction.
Can you remind me how that works?
Sure. We start by assuming the opposite of what we want to prove. In this case, we'd assume that n is actually less than or equal to n2.
So we're setting a trap, assuming something that we think is wrong.
Exactly. Then we carefully choose a specific value for h that would lead to a contradiction, a mathematical impossibility. In this case, they show that for a particular h, the determinant of b would have to be both positive and negative at the same time.
Which, of course, can't happen.
Right. That's our contradiction. It means our initial assumption must be wrong, and therefore n must be greater than n2, and by extension, greater than n1 as well.
It's a powerful way to establish mathematical truths by showing the absurdity of their opposites.
It really is. And they don't stop there. They introduce this value way, which is approximately 2.04998, and in lemma 3.5, they prove that no matter how big alien gets, will always stay less than a.
So n is always climbing higher, but it has a ceiling. What makes this value so special? It seemed to come out of nowhere.
It might seem random, but n is actually the largest real root of a specific polynomial equation that's closely connected to the structure of these matrices. Wu and Yang show that by carefully analyzing this equation, we can see that the determinant of BOO will always be positive for any h greater than I.
So they found a way to ensure the determinant behaves in a certain way just by choosing the right value for a.
Exactly. And because we know that n is the value that makes the determinant 0, it means n must always stay below. It's like it's trapped between two boundaries, always increasing but never able to break through that ceiling.
It's a fascinating mathematical dance. So what are the implications of these bounds on n?
Well, they lead to a really powerful conclusion, which is stated in Corollary 3.6. It says that if we choose an h that's greater than or equal to n, then the matrix B is guaranteed to be generalized positive definite no matter how big n gets.
Wow, that's a powerful result. We can guarantee a certain property for this entire class of matrices just by choosing a large enough h value. We've really gained a deep understanding of these matrices.
Precisely. And this insight has far-reaching implications, especially when we connect it back to those Lie algebras we've been discussing.
Right. This all seems so abstract. Does the paper give any specific examples?
Absolutely. They calculate specific values of n4 and ranging from 2 to 8, and some of them even involve those trigonometric functions we talked about.
Right. I remember seeing that. And they even explain why some values of n can't be expressed using simple radicals. That was interesting.
Ah, yes, that delves into Galois theory, which deals with the solvability of polynomial equations. Essentially, they're showing us that some values of n can be expressed neatly, while others are a bit more elusive, hiding behind more complex mathematical structures.
So we're not only exploring matrices, but also touching upon the nature of numbers themselves.
Exactly, and that's what makes this research so fascinating. It leads us to deeper and deeper questions about the very foundations of mathematics. Are you ready for the main event now?
I think so. What is it?
The culmination of all of this groundwork is Theorem 3.9. It provides a complete classification of when an h-Shuhan matrix with h less than 2 is positive semi-definite, virtually positive semi-definite, or generalized positive semi-definite.
So it's like the big reveal, the culmination of all these lemmas and propositions.
Exactly. It ties everything together, showing us all the possible scenarios based on the matrix's structure and the value of h.
And then propositions 3.1 and 3.11 extend these results to specific types of matrices based on generalized Cartan matrices.
Right. They build upon Theorem 3.9, taking those results and applying them to specific cases.
It's like building a hierarchy of knowledge, starting from those basic definitions and working our way up to these powerful classifications.
A very well-structured approach. And then there's Remark 3.14. They point out a subtle but important point. All of these results about semi-definiteness still hold true if we swap semi-definite with definite and make those inequalities strict.
So it's like they're testing the boundaries of their findings, making sure they hold up under different mathematical conditions.
Exactly. They're showing us that their conclusions are robust and can be applied in a variety of ways.
And finally, Proposition 3.15 brings us full circle, connecting it all back to generalized Cartan matrices and their classification.
Right. It's like we've completed a loop showing how these specific h-Shuhan matrices provide valuable insights into these broader algebraic structures.
It's amazing how Wu and Yang have woven together all these different concepts. It's like they've created a tapestry of mathematical knowledge.
It's a beautiful tapestry indeed, and there's still so much more to explore. Are you ready to continue our journey?
Absolutely. Lead the way. We've gone deep into the world of h-Shuhan matrices, their properties, and those intricate proofs. And now I'm really curious to see how it all connects back to those Lie algebras and generalized Cartan matrices.
This is where Wu and Yang's work really shines. They've connected these seemingly separate areas of mathematics, revealing a link between h-Shuhan matrices and classifying Lie algebras.
Right. That connection has been running through our whole discussion. Remind me how generalized Cartan matrices come into the picture.
Well, think of generalized Cartan matrices as blueprints for Lie algebras.
Blueprints, yeah.
They encode the essential information about how a Lie algebra is structured, the relationships between its elements.
Okay, so they hold the key to understanding these algebraic structures. But where do h-Shuhan matrices fit in?
The connection is actually pretty straightforward. If we take an h-Shuhan matrix and add 2h times the identity matrix, we get a generalized Cartan matrix.
So there's a direct transformation.
Yep. It's a bridge between those two mathematical worlds.
That's pretty amazing. We spent a lot of time talking about positive definiteness and semi-definiteness of h-Shuhan matrices. How do those properties translate to generalized Cartan matrices and then to Lie algebras?
This is where things get really interesting. Generalized Cartan matrices are classified into different types based on their definiteness: finite, affine, and indefinite.
Okay, and those types correspond to different kinds of Lie algebras.
Exactly. Finite-type generalized Cartan matrices lead to finite-dimensional Lie algebras.
Those are the well-behaved ones, right?
In a sense, yeah. They have lots of structure, applications in physics, engineering, all sorts of fields. Then we have affine-type generalized Cartan matrices, which give us infinite-dimensional Lie algebras.
Those are the more complex but equally fascinating ones, right?
You got it. They connect to string theory, conformal field theory. Then there are indefinite type, which lead to indefinite Lie algebras.
Those are the most mysterious ones.
Yeah,
too.
still a lot of ongoing research on those. So we have this spectrum of complexity.
And Wu and Yang's work lets us connect the properties of h-Shuhan matrices to this classification. That's incredible.
Right. It's a new tool to explore the structures of Lie algebras. One of their key findings is that if an h-Shuhan matrix is positive definite, its corresponding generalized Cartan matrix is finite type.
That makes sense. We start with a nicer h-Shuhan matrix, so we end up with a nicer generalized Cartan matrix and a finite dimensional Lie algebra.
Precisely. They also showed that if an h-Shuhan matrix is virtually positive semi-definite, its generalized Cartan matrix can be either finite or affine type.
So we have more possibilities with semi-definiteness.
Exactly. And they don't just give us general statements. They provide specific examples.
I always appreciate concrete examples. It helps to make these abstract ideas more tangible.
Right. For instance, they show that a matrix called BHN with h greater than or equal to 2 corresponds to an affine type generalized Cartan matrix.
So by understanding BHN, we can immediately know something about its associated Lie algebra.
Precisely. And then there's Proposition 3.15. It's a gold mine of information.
Really? What's in it?
It lists generalized Cartan matrices, their definiteness properties, and the corresponding h-Shuhan matrices, all organized based on the paper's results.
Wow, so it's like a dictionary that translates between h-Shuhan matrices and generalized Cartan matrices.
Exactly. It lets us move between these different mathematical worlds. We've come a long way, haven't we? We started with those 3 simple conditions defining h-Shuhan matrix, explored the role of H and its connection to trigonometry, and now we've arrived at this deep understanding of Lie algebras and their classification.
This has been an incredible deep dive. It's amazing how Wu and Yang have revealed these connections.
It's a testament to how interconnected mathematics really is.
It feels like we've just scratched the surface, though. There's so much more to explore here.
Absolutely. And that's the beauty of mathematics. It's an endless journey of discovery. There's always more to learn, more connections to uncover. So, for our listeners, here's a final thought to ponder. We've seen how these abstract mathematical ideas are linked, but how might they translate into real-world applications? Could the properties of h-Shuhan matrices impact fields like physics, engineering, or computer science? The possibilities are vast and waiting to be explored. Thanks for joining us on this deep dive into the world of h-Shuhan matrices. Until next time.